even if it's just a presentation of like, hey, we sat down and thought through this like difficult problem and here's how we came out the other end of it. We had our winning hackathon project in Riga 3 weeks ago was a shell script for Git. So we're not looking for like incredible ideas or a flashy like presentation, but it's like, hey, what kind of ideas can we as a group come together and build and show off together? So that's going to be tomorrow. So the idea is today you meet some people, you make some new friends, you find out what people have to talk about. Tomorrow you come together, even if you've never participated in a hackathon before, put you together and help you find a team. So we'll have a team building thing, an ideas workshop before we get started, spend the afternoon working an idea, and then at the end of the day, it's only 3 hours of work, so it's not much of a commitment. We're not asking for you to give up an evening like some hackathons do. And then at the end of the day, tomorrow, after like our dinner break, we'll give people the opportunity to kind of do expo style. So you'll sit at a table and show off your project. The top 5 teams out of that will show up on Friday and do presentations at the finals. So you kind of have to make it out of the expo to present on stage, no pressure. Cool, and we've got some prizes. We'll have a kickoff on Thursday morning though with more details about how it'll work and all the rules and what to expect and how you'll be judged. So expect more of that tomorrow. Great, okay, a few more announcements from me and then we're gonna have a short break before we start our morning and I guess for an afternoon now, talks. Everyone should have gotten an agenda schedule in your handouts when you checked in, but if you didn't, we have some. It's also up on the website. Great. Okay, some more announcements. We're in main stage now. You came up the stairs, or maybe you came down from the 4th floor to get here. Across the hallway is another stage called the talk stage. So on this floor, you can expect to have the main stage, which is where we are now. Across the hall is the talk stage, and we're on floor 1. If you take the lifts or go up the stairs to the very top of the building, we've got the workshop stage and something that we're calling the annex, along with some snacks and coffees. So that's a good place to take a break if you need to do some work. While you're here, there's some tables up there, and the workshop stage is also on the top floor. So this is where all the activity will be taking place the next couple days. What else have I got? Oh yeah, no photos, please. Or if you are going to take a photo, please ask the people that are in the picture to get their permission. We're of course going to be filming all of the talks. This stage will be live streamed. The other stages will be recorded and posted later. So if you're talking and you don't want to show up on the live stream, please let someone know before your talk. But otherwise, yeah, so no photos. We'll be putting out information. I think there's already some stuff like the pictures of the venue and the schedule if you didn't get a copy are in the Telegram group. So that's a good place to hang out. It's the same for like all of our conferences and we just have channels, etc. So that's a good place to stay up to date about what's happening here at the venue as well as what's happening at future events. Someday we will move off of Telegram onto the great Nostr frontier, but not today, unfortunately. So in the meantime, this is a great way to get information about what's happening. I also had a request that I advertise BitChat to all of you. If you're not familiar with what this is, it's a local peer-to-peer Bluetooth chat app, which they just added some more global chat features to, but originally it's meant for in-person communications, etc. We might be using it to take questions for presentations. We'll see. It's kind of an interesting way to get info, etc. We had a request to try and see if we could break the record of 40 people on BitChat at the same time in the same place. So this is a cool app to try out if you haven't. It was made by some people in the Nostr community along with Jack Dorsey, noted hacker and entrepreneur. Great. Okay, I think that's everything for me. I'll give a short, I think maybe like a couple minute break and then we'll get Robin up for the first talk.
One reminder, if you haven't yet registered, please go to the 4th floor for registration. Before content begins at 1 o'clock, we have talks on all 3 stages beginning at 1 o'clock. Robin on the here, Hubertus on the talk stage, and Barat on the workshop stage. So please go and register before 1 o'clock. Thank you.
Cool. Thanks, guys. Thank you.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025.
Scaling edition, beginning in just a few moments here on the main stage. Ladies and gentlemen, the creator of BitVM, Robin Linus. Please give a very warm welcome. Thank you.
Yeah, hi everyone. It's a great pleasure to open this conference with the first talk for today. I'm going to talk about BitVM, better Bitcoin bridges, and in particular, garbled circuits. I think you're gonna hear a lot about garbled circuits this week. I've seen many talks are scheduled. So I'm going to give like a very high level overview of what's going on in the BitVM world regarding garbled circuits. First of all, I'm gonna give you a quick rundown what BitVM actually is. Maybe not everyone has heard of it. BitVM, first of all, it's a solution to bridge Bitcoin to second layers. So sidechains, rollups, and in general, it's a scalability solution. And how do we do that? Well, we do that by optimistic snark verification. Actually, we would love to have a snark verifier in Bitcoin, but since Bitcoin is very hard to change because people are always busy about fighting about op return or like filtering out spam, we are too busy to actually have to activate a snark verifier, so we need to hack it into Bitcoin somehow. And BitVM is a solution to do exactly that and to do, well, we cannot quite verify a snark, but we can optimistically verify a snark, which is as good as actually verifying a snark. And the rough concept how it works is we have operators that operate the bridge and they process withdrawals when people want to withdraw money from the bridge. And if they are malicious, if they do some kind of funny business. If they want to like withdraw money that they should not withdraw, then challengers can slash them. That's roughly the mechanism behind optimistic verification. And the security assumptions are that as long as we have one operator who is live, then the bridge is live and people will eventually get their money. And we get safety as long as there's one honest challenger. And that is an improvement over the state of the art or the previous state of the art. Here we have a 1 of n assumption. Previously we had a T of n assumption, and 1 of n is obviously way better. BitVM2, the precursor to all the garbled circuits thing, the BitVM Alliance worked on it for about a year, and we implemented it all. It's 9 companies that are in the BitVM Alliance right now, and we completed the first implementation in March. It's all open source, MIT license, you can use it if you want. And we just completed a security audit, like almost, like we are in the very last steps to actually fully complete the security audit. And soon, within like, hopefully, I don't know, next month or 2 months, the first BitVM2 based L2s are actually launching on Bitcoin mainnet. Well, the funny thing is, we had just completed BitVM2 and thought this is the solution now, and then the entire garbled circuits hype started. And it started with Jeremy Rubin publishing the Delbrag paper in April. And like 2 days later, he garbled circuit pilled me at MIT Bitcoin Expo. I had been working on something similar a while ago, and that's why it took him only like 2 or 3 sentences to make me realize BitVM2 is completely obsolete, which was a funny realization because we had just completed it. We just paid like tons of money for the security audit, and then Jeremy came to me when we were like scribbling stuff on a whiteboard, and he just talked 2-3 sentences to me, and I realized, okay, an entire years of work is kind of obsolete now. And then Garbled circuit pilled the entire BitVM Alliance, and then it turned out Liam, the great Bitcoin cryptographer, had already working on garbled circuits for quite a while, and then he resumed all the cool stuff that he had already been working on. And also Fairgate, they had been working on it. I think you hadn't published something yet, but you guys had been working on it. And it's kind of funny that so many people had the same idea at the same time. And yeah, the research around it exploded. Like all of the BitVM companies immediately pivoted to researching garbled circuits. And now many different directions are getting explored, and it's very exciting to be part of that. And a fun fact is that this was already possible in 2017. So all that stuff that we had for BitVM2, like all the taproot stuff and like all the complex stuff, is actually completely unnecessary. SegWit already activated all of that, and we could have had snark verifiers in Bitcoin since 7-8 years. It's quite funny. And also it also makes you wonder what other things are possible that nobody has figured out yet and that are actually easy to do, but we just haven't figured it out yet. So what's the difference actually between BitVM2 and the garbled circuits style? Well, BitVM bridges, they consist mainly of 2 different parts. First of all, the snark verifier, and the second main component is the bridge contract. And garbled circuits, they make the former, the first one, the snark verifier, way more efficient. However, the bridge contract essentially stays the same. It's essentially, not essentially, it's pretty much the same thing. So garbled circuits are more or less a drop-in replacement for the BitVM2 style verifier. And there's that term BitVM3. It's essentially take your BitVM2 bridge contract, add garbled circuit snark verifier, and then you get like the BitVM3 thing. And why is that so amazing? Well, here's the comparison. In BitVM2, like the main 2 transactions that we have that make the most of the cost are the so-called assert transaction and the disprove transaction. The assert transaction is the operator asserting to approve, and the disprove transaction is a challenger executing or like slashing the operator. And in BitVM2, it was 2 megabytes for the assert transaction and 4 megabytes for the disprove transaction, which makes 6 megabytes in total. And that's, of course, a lot. It's 1.5 blocks. Very expensive. You actually don't have to do it. Like, it's not necessary to do a withdrawal. Like, if you want to do a withdrawal, you don't have to put 6 megabytes on chain. But you have to be able to put them on chain if somebody is lying. That's the optimistic part. So this is not the actual cost, but it's like the worst case cost that you have to be able to pay. And in like the Garbled circuits approach, it becomes way more efficient. The assert transaction goes down to 70 kilobytes, but the disprove transaction is just 200 bytes. It's just revealing a hash pre-image. And it is, of course, orders of magnitude better. It's roughly 1,000x improvement over the BitVM2 approach. That was also why, when Jeremy told me about it, I was like just mind blown that this is possible. Because we were thinking about like how to get it down from like 6 megabytes down to 5 megabytes or something, and then suddenly we get it down to 70 kilobytes. Now, how does that actually work? How does that magic work? I think it was Liam who coined the term conditional disclosure of secrets. It's quite funny. Garbled circuits, they have been invented for privacy reasons. We're kind of like using them incorrectly. We are not using them in the way they were intended to be used. It's kind of like a side effect that you can use them for conditional disclosure of secrets. And what do we mean by that? Well, during the setup, we agree on some kind of black box. For now, it's just a black box. You don't have to care too much what it does. And the operator, they can publish a snark, and then anyone can feed this snark proof into that black box. And if that snark proof was incorrect, then that black box reveals a secret. If that snark was correct, then that black box essentially does nothing. But if that snark proof is incorrect, then that black box reveals a secret. Yeah, as I said, like during setup, they agree on that black box. Then the assert transaction becomes the operator committing to a snark proof. And disproving means that the challenger, they evaluate that snark using that black box. And if the snark is incorrect, a secret is revealed. And the knowledge of that secret is essentially the fraud proof. If I know that secret, that means the operator lied and committed to an incorrect proof. And that's actually what it makes so efficient. I don't have to disprove any kind of computation anymore. I just prove to the chain that I know that secret, and that is enough to prove that the operator actually lied. And how does that work? Well, here is a truth table for AND. Like we're essentially to garble a circuit, we have to know how to garble a single gate. And here the example is an AND gate. Maybe you've heard that you can like decompose any kind of computation into logic gates, into AND, OR, NOT, XOR, stuff like that. And they can all be represented with such truth tables. And here we have A and B equals C. And you see these truth values here. I'm not going to read them out, but actually, it's wrong, right? so I should better not read them out. I will leave it for now. I'm gonna destroy the animation if I'm fixing it now. So yeah, it's the one should be in the lowest row.
Robin encouraging you to not trust but verify, of course.
Yeah. So. This is just a regular truth table, and now how do we garble it? Well, first of all, we replace these values with so-called labels. Labels are just like random data, like pre-images, hash pre-images. Yeah. So instead of writing 0, we just have like, let's say, a 20-byte random value there, and they are secret in the beginning. And what we actually wanna express is that. If you know the secret value A0 and the secret value B0, then you should learn the secret value C0. If somebody publishes, like that's how that works, like in the assert transaction, somebody publishes inputs, and those could be, for example, A0 and B0. And when you learn these two, then you should learn C0. And how do we do that? Well, we use an encryption scheme. On a very high level, it's just you have two functions. The encrypt function, it takes a key and a message, and it puts out a ciphertext. And the decrypt function takes a key and the ciphertext and returns the message. And to garble the table, what we do is we use that encryption function, and we produce 4 ciphertexts. And it's just that C0 is encrypted with the key A0 and B0. C0 is also encrypted with A0 and B1. C0 is also encrypted with A1 and B0. And C1 is encrypted with A1 and B1. So if you learn any assertion to A and B, you will be able to decrypt one of these rows and then learn either C0 or C1. And this is one way. So you only learn one of C0 or C1. You never learn 2. That's very important. And this is essentially the key mechanism behind garbled circuits. However, I glossed over that actually you need verifiable encryption. I have to prove to you in the beginning that these encryptions are actually correct. Because if I give you just some random ciphertext, you don't know anything about them, and you don't know if they actually decrypt to these values if you learn the keys. So we need so-called verifiable encryption that allows you to verify that the ciphertexts are actually decrypting to what I claimed that they will encrypt to. And that's also what makes everything complicated in the end. But given that this works for now, we just assume we have some kind of verifiable encryption scheme. Then we have a nice primitive that we can now compose. We can express all kinds of gates, like any gate that we want, XOR or whatever you have, can be represented using this. And then we can compose them, because in the next gate we could have, for example, C, D, and E. So C and D equals E. And then we just use the labels of C in the next gate. And so we can compose these gates. And then we can compose garbled gates into garbled circuits. And then we have that nice property that once input labels to the circuits are revealed, they reveal a particular corresponding output label. And in the case of a snark verifier, that means, we want to have a snark verifier because that enables universal computation. We just have a single circuit, and that circuit allows us to verify any kinds of computation because it's a snark verifier, and a snark can verify any kinds of computation. And a snark verifier on a high level is, you have a function, verify, and that takes a proof, and then it returns true or false. Very simple. And the protocol is the bridge operator. They publish a snark proof, and those are the inputs to that circuit. So they actually publish every bit of that proof, and then you can feed it into that circuit, and then the challenger verifies that circuit, and they verify that snark, and if the snark was incorrect, then they learn the output label for false. And that is the fraud proof. Now, what are the issues with that actually? Well, a snark verifier, at least like the most popular snark verifier with it, which is Gross 16, it's about 10 billion gates. So that's a lot of garbling that we'd have to do. And so we have these off-chain costs that are the main issue here. And they depend mostly on the circuit size and the time, or like the properties or the performance parameters that we have is, on the one hand, the circuit size, then the time that it takes to garble the circuit. I'm not sure what I meant here, but yeah. And on the other hand, we have on-chain costs. We can do a little bit of trade-offs. We can have more efficient schemes, but then the assert transaction or the disprove transaction becomes a little bit bigger. And of course, another important parameter are the security assumptions. There are some schemes that are more efficient, but they have more aggressive security assumptions, I would say. And there are two kinds of assumptions. On the one hand, we have these crypto assumptions that I just mentioned, and on the other hand, there's also if you had some kind of trusted computing thing, like if you have a cloud that you trust, then you can just garble in the cloud. That makes it, of course, way more efficient, but then you have to trust the cloud, and you don't want every operator to trust that single cloud, because then it becomes a single trusted party, and that defeats the entire purpose. So ideally, you want to be able to garble the entire circuit on like your local machine. Now the solutions. Many different schemes are getting explored right now. I think Fairgate is also showing one this week, I guess, like maybe-ish. I got a feeling that there might be something. The most traditional thing is so-called YAO-style garbled circuits, and combining that with the cut and choose method to do the verification. That is like the most simple thing. That is like the least. It relies on the most simple cryptography actually, but it ends up with like quite large circuits, and it takes a lot of compute. Then Jeremy's scheme was so-called Delbrag. Delbrag does essentially optimistic verification, so it doesn't really the verifiable encryption is kind of like replaced by optimistic verifiable encryption. So you get that circuit and you just trust that the circuit is correct, or you just assume that the circuit is correct, and then during if you learn during evaluation that the circuit was garbled incorrectly, then you can use a Bitcoin script to slash the operator. And the issue is that this Bitcoin script is quite large. In the Delbrag scheme, it's about 200 kilobytes, and that kind of it's 1,000 times less efficient than the most efficient form that we could have by just publishing that 200 byte transaction. BitVM3S is a scheme that I came up with, which is essentially an optimization of Delbrag. I'm going to talk about that in a later slide. Then there's another thing called BitGC. That is quite cool because it the garbled circuit at the end is very small, like it's just 100 megabytes or something for a snark verifier, but garbling is very expensive, and proving it is even more expensive. Then there's like some kind of like bit esoteric thing called attribute-based encryption. That would be pretty cool if it would be practical, but I think it would take like a month or something to garble a circuit using attribute-based encryption, but it would be extremely compact at the end. And then there's Liam's scheme, which I think is the best scheme that we have so far, called Glock, and I think he's going to give a talk tomorrow on Friday. I'm not quite sure. I thought it was Friday, but he said it's tomorrow. Yeah, and if you want to learn more about that, there is that paper, BitVM with Succinct On-Chain Costs by Wai-Kang Chen, where he summarizes the different solutions that we have for garbling snark verifiers. A few classical optimizations are, first of all, free XOR gates. What's funny is that you can garble gates such that the XOR gates are free. You don't have to communicate any data for the XOR gates. And so you are trying to build a circuit such that you maximize the number of XOR gates. That's actually also what makes Liam's scheme so efficient. He came up with a way to like have a particular snark verifier that consists mostly of XOR gates, and that makes it extremely cheap to garble. But it's also compatible with, I think, all of the other solutions. Another cool thing is half garbling, and in particular privacy half garbling. That means instead of communicating 4 ciphertexts per gate, maybe you remember we had 1 per row, you can essentially communicate just a single ciphertext per gate. And that gives you a roughly 4x improvement. For the garbling itself, you can use hardware acceleration, in particular AES. Most CPUs have that today, and that makes garbling orders of magnitude cheaper. BitVM3S is that thing that I came up with. It's, as I said, optimistically verifiable garbling. you commit to the entire circuit in a taproot, like you have a huge tree, and in that tree you have one leaf for each gate. And if during evaluation you learn that any gate is faulty, then you can essentially execute that gate on chain and slash the operator. So that's the same principle as Delbrag. However, here it's way more optimized because there are two tricks. First of all, BitHash and using Prince v2, which essentially brings down the cost to on the order of like 10 to 20 kilobytes. Which is also like, since the cost is dominated by the assert transaction, that's quite decent. There are many different implementations of the approaches that people are currently exploring. First of all, the BitVM Alliance, in particular Citrea, they have implemented a Gross16 circuit that is available on GitHub, just github/BitVM. And I think Babylon has optimized it a lot. David's going to give a talk tomorrow about it. Probably you can learn more in his talk about their implementation. And then there is also an implementation of Liam's scheme, the Glock scheme, which he will present tomorrow. Another important dimension is the bridge performance. First of all, the collateral cost is the most important performance parameter in the bridge. In BitVM2, it was like you had to put, I don't know, $10,000 or something, $10,000 to $20,000 collateral, which is of course a lot, and that means not everyone can become an operator. In BitVM3, the collateral cost goes down to less than $100. And the cost of a dispute becomes like negligible. In particular, if you're using a bridge where you're pegging in like more than 1 BTC or something. Like if you're pegging in $100,000, it doesn't really matter if you have to put if you have to use like $100 or something for a dispute. Another important performance parameter is the throughput, like how many withdrawals can you process per week with your bridge. And also the capacity, so how many deposits can you actually have in your bridge? That is, since in Bitcoin we don't have actually like a smart contracting language, it's very limited. We have to hard code everything, like we need to pre-compile contracts for everything that we want to do. So the number of deposits is limited by the number of transactions that we have pre-compiled. Yeah, and the prover performance is also very relevant. Like how expensive is it actually to prove your L2 to the main layer? And in that field, many different designs are getting explored. I think every of these companies in the BitVM Alliance, they are exploring like slightly different approaches, and it's quite interesting with like what kind of solutions they come up with in that design space. Now, outlook. BitVM3 bridge contracts still have the same drawbacks. Like we need some kind of trusted setup for the covenant emulation, and that sucks, of course. And it would be quite cool if we had some kind of covenant proposal or like some covenant opcode that would allow us to get rid of these trusted setups. It does work with CTV. However, it's very hacky because you have to use like legacy scripts, and people don't want us to use legacy scripts. TXHash would be the clean solution. That would be ideal for BitVM actually. Also, people are discussing template hash, but that doesn't help at all. Actually, template hash is specifically designed to not support the hack that we want to do with CTV. They find the core devs found our hack so ugly that they thought they have to change CTV to make it incompatible with our hack. In the long term, we would actually also want to get rid of these operators that would require something like opmal. I guess that would be like the minimum that we would need, but probably great script restoration that would completely solve it, then we could have just Ethereum-style snark verification. Or even better, if at some point simplicity would get activated, that would also solve everything. And we could completely get rid of all these kind of hacks. Well, I guess it's beyond the scope of this talk to talk about the downsides of simplicity, because simplicity has a lot of complexity. Yeah, summary. BitVM 2 is almost production ready, and soon we're gonna see the first launch, like L2 is launching on mainnet. However, it's pretty much obsolete. At least in theory, it's been made completely obsolete. Garbled circuits and BitVM 3, they are the future. They are just like vastly better in pretty much all dimensions that matter. They are 100 times better in on-chain cost and essentially reducing the cost of dispute and everything. The main challenge is to tame the off-chain cost. It's costly to garble and to communicate these garbled circuits because they can become quite huge. And many directions are getting explored right now, and there's lots of exciting research going on. Essentially every day people come up with like new ideas and new optimizations, and it's a pretty exciting development. Yeah, and that's it. Thanks.
Thank you. We have lots of time for questions, so ladies and gentlemen, please raise your hands if you have any questions for Robin. I'll come to you.
For the process of garbling a circuit, does this need to happen only once when a bridge is created, or does this happen multiple times?
Oh yeah, good question. Actually, you can design the bridge contract such that you need it only once. That is because since these challenges are also permissioned, you have a fixed set of challengers and a fixed set of operators. Each pair of operator and challenger, they have to have only a single garbled circuit. And if they ever have a dispute, then that means one of the parties is dishonest, and then they get slashed, and then you don't need any other garbled circuits. So, yeah.
Thank you.
Can you explain at a high level what logic exists inside of the bridge contract?
Here's a different talk, and here I have some slides. Let's see. So the key idea is to introduce state using connector outputs that were popularized by Burak. So this is like the main primitive behind the bridge. You have some kind of parent transaction and then a conditional transaction that depends on the condition transaction. And the parent transaction creates an output, and let's say Alice, she pre-signs that output using sighash all, committing also to the output of the condition transaction. And the condition transaction didn't happen yet, but she knows in advance what the transaction ID will be. And then she essentially makes this transaction depend on this transaction being executed. So she essentially says, you can execute the conditional transaction exactly if the condition transaction hits the chain. And this output, we call it a connector. And here we can actually encode logic, because if we have some kind of alternative transaction spanning that connector, then it makes it impossible to execute the conditional transaction. So we can essentially encode a conditional, like an if statement, in transaction. So you can execute the conditional transaction exactly if the condition transaction was executed and that connector was not destroyed in some way. And this is like the main primitive behind the bridge. In the bridge, we have the peg-in transaction or the deposit transaction, and here that trusted committee, that N of N committee, they pre-sign the packout transaction, and the packout transaction commits to 2 connector inputs. And those connector inputs are outputs of the kickoff transaction of the operator. So once the operator wants to withdraw money from the bridge, they execute that kickoff transaction. And the first output is time locked for 2 weeks, which is essentially the challenge period. So he cannot execute the packout transaction before he has waited for 2 weeks. And then here we have that connector, which essentially encodes the logic. And here BitVM is just a black box. But if you win the BitVM game, then you win an output that allows you to execute the slash transaction. And then the operator cannot execute the packout transaction. And this setup, you have it for each deposit for each operator. So since you assume that one of the operators is honest, at least one of them will eventually execute the packout transaction. And all the dishonest ones will get slashed using this mechanism.
And the thing that gets leaked by the Garbled circuit, the secret is something that makes like either of those inputs bendable? In the slash?
Well, this is kind of like the high-level idea behind any kind of BitVM bridge. To make this compatible with garbled circuits, you essentially would have a transaction here that is spendable if you know the secret.
Thank you.
So you said there is just like one circuit that's garbled per pair, right?
Yes.
Doesn't that have to be reusable? Because you might have multiple deposits, or is it just when you slash when you slash an operator, he just goes out of the N of N, right? Or
like you only need that garbled circuit in case of a dispute. If no dispute happens, then this game is not executed at all. The operator just puts the kickoff transaction on chain, and he waits for 2 weeks, and nothing happens. So only if there is a dispute, you need that garbled circuit. And if there is a dispute, then one of the 2 parties is dishonest, and they get slashed, and that means that pair will never have to have any kind of dispute again.
So he gets kicked out of the committee, basically.
Yes. Yeah.
Okay.
Let's just thank Robin again for his great talk and questions. Thank you.
Thanks.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025.
Up next, we have Building Advanced Protocols with BitVMX from the BitVMX Principal Engineer, Martin. Please give a very warm welcome. Thank you.
Yep. Okay. Hey, hello everyone. Thank you for having me here. Well, today we are going to present building advanced Bitcoin protocols with BitVMX. I mean, the idea is that we are going to talk about BitVMX as a platform for creating other applications on top of it, and we are going to explore the components that helps on these different type of problems that we will need to solve for creating these type of applications. Then we will move into some of the innovations that we did. Yep, let's start. So what is BitVMX? Well, first of all, I think obviously we saw the previous presentation from Robin. 2 years ago, he presented BitVM. That way opened the door for a new type of smart contract on Bitcoin using disputable computation. This actually was possible even without changing consensus on Bitcoin, what wasn't possible before. Basically, the idea, I mean, the BitVMX is a little different on the other version of BitVM. It's not like BitVM 1, 2, or 3. It's a completely different implementation that is based on a RISC-V emulator. The idea is that instead of the verification being executed directly on chain with a Groth16 verifier, we are running a program that can be verify any type of verifications that we decide. In particular, we are using Groth16, but this is just because of the it is in a way reduce the size of the inputs of the programs that we want to verify, and that's the reason chosen. But also one of the possibilities that provides having a RISC-V processor in a way that we can, in example, verify a counterproof given by another party, right? I mean, the prover could provide a proof, and the verifier can provide a counterproof, and those will compare, and that's what part of the flexibility that gives the idea of having a CPU for running this. In particular, this has been shown too, but the idea is that always these kind of protocols have a happy path where if both parties agree on off-chain, they could basically sign a new transaction that will move the funds from the locked funds in the previous locked in the UTXO. And if in case of dispute, in case there are no agreement there, there will be a dispute on chain, but only on those cases. Just one other thing, that because it was a comparison between regarding the sizes of the cost of running a BitVM2 that was about 6 megabytes, or in worst case, BitVMX as it is today is around 600 kilobytes. I mean, it's much smaller, the cost on chain. It's at the expense of having another set of rounds of challenges, of transactions, but the cost today is already much closer of what would be a Garbled circuit version. I want to talk about two applications that we already built using BitVMX. We have designed two bridges. One for Rootstock, like it's a bridge between Bitcoin and the Rootstock layer 2 blockchain. It's an improvement on the assumption of security. Their previous bridge has a committee of around 11 operators that you need to have more than half of those operators to be honest in order to the bridge to be secure. This implementation using BitVMX reduced that to 1 of n honest assumption, and also allows you to increase the number of operators, because you don't have like a problem where a lot of operators can gather together and collide together to reduce. Actually, increasing the number of operators increase the security. And on the other hand, we have the Cardinal protocol. That's another application that we build using BitVMX. The idea is that we can, if you have an ordinal or an FT on Bitcoin, you will be able to log this on OTXO on Bitcoin, and it will enable you to trade this NFT on Cardano network, right? I mean, you can, for example, put it as part of a loan on Cardano, and then get back into Bitcoin later after trading or whatever you want to do, or DeFi application that you need to run on there. Also, it's a one of n honest assumption, and something interesting is this using the transfer of owner protocol transfer of ownership protocol. The idea of this protocol is that there is no time in the process of all the breaching that the ordinal gets in the hands of the operator. So there is no risk that the operator will take the ordinal the cost of this can be varied. So it also reduces the need of having a collateral as part of the operators. So these are some design decisions that we took in order to, when we start working on the implementation of BitVMX, we wanted to have something pragmatic. The idea is to have to be able to release real life and production grade code. We didn't want to have like a POC or a theoretical implementation. We have something that other parties can use and build on top. So it needs to be robust in that sense. We wanted to be protocol agnostic. The idea is that actually what happened, that we are not tied to any of the breach particular details for implementing this. So again, I mean, we were able to implement 2 solutions on top, and we are in the process, and we could implement other solutions. We are not tied to any of these. Modular, because we wanted to reuse the components that we write, we are able to switch them, and in general, the solution is presented as modular for us to use it. Fault tolerant, we have to create this and say in a way, as Robin mentioned, I mean, all the breach you need to have like a whole graph of transactions that control the logic of the smart contract that you build, and in a way, if you lose any of this information that you generate on setup, you probably won't be able to regenerate that. So we need to have very robust infrastructure to support that and don't lose anything and continue. Adversarial robust. I mean, the idea here is we are gonna be doing a setup. I mean, during the setup phase of the protocols or these applications that we build, you usually have to collaborate with other operators in order to generate the smart contracts. The thing is, these communications needs to be secure, because actually the same operators that you are trusting in that time for the setup could be adversarials that are trying to attack you. So the security measures needs to be in place for this to work well. Scalable. We are supposing to be, I mean, one instance of BitVMX needs to be able to handle up to thousands maybe of locked funds. In the same instance of BitVMX, BitVMX will control one instance of BitVMX needs to be able to control a lot of these of TXOs. And not for us less important, is we decided to use standard transactions. We didn't want to be in the situation of needed to use one specific mining pool for being able to send our transactions. That in a way makes the problem of censorship bigger, right? I mean, if you only depend on one particular pool that will send your non-standard transactions. So all the protocol is designed with standard transactions. So for the building blocks of BitVMX, we have we needed to have something to run this verification execution of chain of the information of the parties. We need then something to have the validation on chain. We need something to help on the proof generation. We're using RESET for generate the proof, but the thing is, the time to generate the proof usually takes may take hours. So how exactly this connects in the architecture to generate the proof, get the information back, and put this as part of the input of the program is important. We need to generate a graph of transactions that needs to be agreed on setup. We need to have persistent storage. we need to have transaction signing, and for the transaction signing, it's not only the signing of the transaction, the regular Bitcoin transactions, but we also will need to use Winternet's one-time signatures. That's the way to encode the information into these smart contracts. As you might know, Bitcoin script doesn't have reflection on other transactions. You cannot go and get the input that other party put in one transaction, take it and use it in the next transaction. So for solving that problem, we are using Winternet's one-time signature is the way to use those kind of connectors that Roy mentioned. And so we need to have something that handles this type of signatures too. Then we have obviously something to connect with, handles the Bitcoin connection for monitoring and for dispatching transactions. We need to have connection between subsystems and connection between operators. On top of that, obviously, there is an orchestration of all of this. Well, in this graph, if you can see, we have in the yellow boxes, we have like the external parts that of the system, Bitcoin, the Bitcoin core, the Bitcoin network. There is 0 instances that will generate the zero knowledge proof. We have the protocol layers that will be built on top of BitVMX, and on the top right, right there in light green is the rest of the operators. In the center, we have like the whole BitVMX instance controlled in the center by the BitVMX client, and what is around is the rest of the components for communication, for key manager. We will see those on detail. So one of the main components is the BitVMX CPU. Basically, this component serves 3 main purposes, being like maybe the first is the execution of chain of the input provided by the prover. Then we need to have something, as BitVMX works, at some point we will need to try to find, in case of challenge, we need to try to find like one step that we agree, both parties agree, and one step that there is a disagreement. And the idea here is that the only thing that we need to be executed on Bitcoin will be one of the opcodes of RISC-V, and for that we need to have all the RISC-V opcodes mapped into Bitcoin script. That's something that also this module has implemented. And on top of that, also this module is responsible for handling the logic on all of these disputes, trying to find the dispute step and to choose in the set of possible challenges that are maybe required to challenge an operator in case it's malicious, and also help the prover to, if it's the honest one, to respond in the right way to actually win the challenge if it's badly challenged. Okay, protocol builder. So, as we mentioned before, all of these protocols or applications that we build up are mainly based on a big graph of pre-signed transactions. And building this transaction is not easy. And what this module does is, in a way, abstracts the part of creating the nuances of the Bitcoin transactions itself, and allows you to design the connections. I mean, it's more focused on the logic that you want to achieve with the protocol itself. So this is the main purpose of the of the protocol builder. It allows you to, as I mentioned, do this to create different types of transaction. It stores metadata that will be used in order to sign those Winternet's transactions or decode those Winternet signatures from the transactions seen on chain. It helps in the creation of jailbait for parent transactions that are used for actually ensure that transactions are sent on chain. It's also help on dust and transaction fee calculation. As I mentioned, this is our big graph, may have different branches, or it becomes very difficult to do by hand the computation of how much dust and the transaction fee you need for this. And also it has some interesting debugging capabilities to show and to visualize the graph itself produced by the protocol builder. For storage, we are using RocksDB as backend. It's a key value database. We choose to this because it's very performant, supports transacted operation. That is key for the part of being fault tolerant. It's simple and in a way also agnostic and gives you the flexibility for the other applications that are built on top to store information without requiring to have like a more structured database for doing that. On top of that, we have an encryption layer for storing keys or partial signatures or important information that cannot be disclosed. We have a key manager. It handles the key generation and handling of these keys. We are not only supporting ACDCA, ISNOR that are obviously required for signing the transaction, but we are handling all the MUSIC2 protocol for aggregated signatures. This protocol allows you to have like one signature more efficient than have like another type of multi-sigs on Bitcoin. But for doing this, you need a kind of round protocol where the party sends its public key, then it sends the nonces, and then you may need to share partial signatures. So this is handled in part by the key manager. Then it's of course, as I mentioned, the winter needs one-time signatures, and finally RSA, because we need, as I mentioned, to have secure communication between operators and between subsystems. So we have a way to sign this using TLS. So for the Bitcoin components, we have an indexer. It's actually 3 modules. Are the indexer to keep track of the state of the blockchain and have the indexed information that helps to other modules to work fast and more efficiently. We have a monitor. Basically, the monitor, once we build this huge graph of transaction, is responsible of tracking the transactions on chain. What this means is, for example, we need to be able to react in the time that we saw a transaction from an operator claiming that he owns a specific UTXO. So it's important to have a module that is responsible for tracking this and notifying this information in case of it's happening to the upper layers. In some cases, we need to track external transaction because, for example, when some external user wants to put money on the bridge or needs to send something to on a specific UTXO, they might be informing by other means from transactions. So we need to be able to track this transaction and see if they are present on the blockchain. And of course, we need to be able to confirm the state of our own dispatched transactions. Also, we have a coordinator module. That is the one that dispatches the transaction requested by BitVMX and may send transactions of the application that's built on top. This also ensures that the transactions are sent, and if there is always there are a jailbreak for parent transaction to make sure that the transactions are sent, because we cannot predict the fee of the transaction beforehand. So this module ensures that the jailbreak for parents are replaced by fee transactions are put on chain and handles the increasing fees if necessary for ensuring dispatch. For communication, we have created a message broker between to send message between modules and also between operators. We are using it's based on TARPC. This repository from Google that handles remote procedure calls. And the idea is that we have this communication encrypted with TLS. We also have we are handling PNet certificates for the client and the server, because we also have allow list and routing conditions, because in a sense we need to make sure that the users that the bridge informs, that the operators that inform that are able to connect or to set up something are the only ones that can be connected, and not others, because it's a security risk on have open ports and stuff. We use this module, as I mentioned, to connect not only with the rest of the operator, but to connect subsystem being the other application built on top, or the RISC-0 generation module, or the CPU itself. Okay, the RISC-0 proof generation helper. Basically, the idea here is, as I mentioned, the generation time of the zero knowledge proof usually may take hours, and may take hours running on a specific hardware. So having a specialized hardware on Amazon instance is something that you may require on these types of setups. So the idea is that this tool will, in the moment that there is the necessity for generating some proof, will start the instance, will generate the proof, and then will turn it off again, because the price of having those kind of instances running all the time doesn't make sense. Okay, and the last component is the BitVMX client itself. It handles the request and made by the operators protocols made on top. The idea is that it has an API to connect with the other applications. It helps on the setup of these protocols, or orchestrate the rest of the modules to communicate itself, to be able to exchange the keys, the signatures, could pre-generate the graph needed for this kind of disputes, and then of course is able to track this transaction and help on automatically resolve the dispute of the dispute channel part of the transactions. Well, so for Garbled circuits, BitVMX will be supporting it. It will be integrated in future versions. The idea of having BitVMX made in a modular way is that we were able to switch components easily. Probably the only component that we may need to change is the CPU, and probably modify a little bit the dispute channel to work with Garbled circuit. But the rest of the components will remain the same, and their integration with the applications built on top probably too. So what we want to enforce or try to show here is that BitVMX is like a platform that allows you to build on top and kind of forget what's the solution that you have there as an engine to solve this kind of dispute. We are open sourcing. We started open sourcing all the protocols. The protocols. No, the repositories. We started some time ago. We will end up open sourcing the rest on the next month. We are also creating an SDK. This SDK will help and simplify the ability to create other applications on top. We'll be presenting this probably soon, and also with some front-end example to help you create some application on top. So now the idea is to present some cool stuff, some cool ideas that we think that we found during the process of implementing BitVMX. Yeah. Let's see some of those. First, there is we created something that we call claim gates. There is a problem that exists when you have a big graph of transaction with different endpoints that will end up with the same result. I mean, for example, you can have maybe several timeouts transactions that needs to be executed, and these claim gates, the idea is that will help you to reduce the number of transactions needed to connect this action, the action that we need to execute for these different ends, right? So avoids replicating a lot of information. Also reduce in case of depending on the time locks of these transactions, usually you have several time locks depending on the stage, and the thing is, this protocol will, or subprotocol, or will allow you to just use the minimum of those time locks. Okay, so let me show you a little bit how it looks. I hope it's readable. I don't know, maybe. So on the top, we have a protocol, a sample protocol that could be a dispute between Alice and Bob. The idea is like usually you have turn-based transactions. So for example, Alice is on greens trying to send a transaction, then is a reply from Bob. But if Bob doesn't reply on time, then there is a chance of Alice to penalize Bob for not putting this input on chain. And these kind of things happen all the time in a lot of transactions. And the thing is, usually what you want to connect is this for a specific result or a specific action, or actually taking the funds. But this makes, if you need to tie this every of these cases of success, you end up having replicating a lot of transactions. So for that, in the bottom here we have the claim gate. The idea is at any time Alice could make a claim. The claim in this case is I won, right? And if you see there is a yellow box from Bob that says Bob stops Alice. So the idea is, if Alice actually didn't won, there is a pre-signed transaction that would allow Bob to penalize Alice immediately, right? That's the idea. So how Alice can actually put this claim on chain? Well, for that, first it needs to consume the enabler that will allow Bob to stop her. So the simplification is that you only need to consume that simple be out from the transaction in each of the cases that actually Alice won, and then you have a claim gate to actually perform the execution of the action. Yeah, after in this part, if after time lock Bob cannot claim that Alice didn't want, Alice can put the Alice won success transaction. We have some enabler that will actually allow her to execute the action that you want. In this case, maybe taking the funds, or maybe other claim gates that can be chained together. We have this is another thing. This is a library that we have created the last year. Basically, it's a library that helps creating Bitcoin scripts. We have used this to implement the optimized version of Blake 3 and SHA-256. This library is, these algorithms are the ones that are being used currently by BitVM2. We use it too for creating all the RISC-V opcodes and to create the dispute channel challenges. What are the key features of the library? The idea is that when you want to write Bitcoin scripts, in the moment that you start moving elements from the stack, it starts becoming very difficult. I mean, it's complex to manipulate the elements, because they start moving and you need to track where those elements are, and it's difficult. So what this stack tracker permits is to define some kind of variable or struct that will point to a group of these elements and will allow you to operate with them. In a sense, you can move them together, you can split it, you can access some part of it independently. It's really, really helpful. And also, we have a debugger. I was inspired by Johan Halset. I think I saw him here before. He presented something similar in Austin last year. Basically, having the ability to debug big Bitcoin scripts is like a key for doing this. There are a couple of IDs on chain on the web, but they are not good enough when you start doing something very big. And we have an optimizer that solves like small cases of that needs to be optimized from the script, but at the end you end up gaining maybe 1% extra of size, because it removes some silly things like from old stack to alt stack, things that end up being duplicated unnecessarily. So it removes that. This is how the debugger looks like. Not sure if it's more or less clear. The idea is that you can see how the elements moves on the stack to the alt stack and the operation that you are executing. It is open source. You can grab it from there. There is also an article about the optimization of scripts that shows a little bit more about the scripts itself and how it works. Okay, and one more. We have we encountered a problem with the minimum relay fee of the transactions. Basically, the problem was that as we put like really big inputs of the programs into transactions in part of the transaction graph, and as we mentioned, these transactions need to be pre-signed. This also means that the cost for the transactions needs to be paid upfront. I mean, needs to be locked in the UTXO before actually, when in the moment of setup. And doing this force you to, when we discovered this, we noticed that if the witness of the transaction were very big, we end up having a lot of money pre-allocated on the setup, and that was not efficient and was starting to be very costly. So the solution was to move the inputs into the chain pair for parent transactions. The idea here is that we were already using chain pair for parent transactions because you can, in a way, you're impossible to forecast the transaction fee in advance. So we need to send the transactions, being able to pay for these transactions with an independent wallet, and having that enable us to actually move the conditions that were checked on part of the flow of the transactions into the spend of this the chain pair for parent transaction. This reduced a lot the cost of the protocol, making it more capital efficient. We need to add some extra log time transactions to penalize for not putting this input on chain also, but then at the end it's also more efficient. Okay, so that's it for the presentation. We want to invite you to a hackathon that we will be running on Berlin on the Bitcoin++ next October. Yeah, thank you. Well, I think except Samsung has questions. Okay.
No questions. Thank you very much, Martin.
Thank you.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025.
Yeah.
Ladies and gentlemen, continuing the content here on the main stage at Bitcoin Plus Plus Scaling Edition, BRC 2.0 with Binari and Halil. Please give a very warm welcome. Thank you.
Hello everyone. Samet. Screen share mı şey yapar mısın? Okay, thank you. Okay, I'm gonna okay. So, hello everyone. Today, we're gonna talk about BRC20s and BRC 2.0. Released on Monday, so it's been a crazy couple days for us. Therefore, we're just gonna show, instead of like going over slides, we're gonna show you live whatever is going on. So I'm Binari, I'm the founder of Best in Slot. Halil is my co-founder, our CTO, and he's the main guy behind BRC20 and BRC 2.0. So to start with, who dealt with ordinals? Like, do people play with ordinals here a little bit? BRC20? Amazing. Okay, so BRC 2.0 is like an upgrade for the BRC20. We are the lead core maintainers of the BRC20 protocol, and we've been working on making it programmable for the last 2 years almost now. So a little bit of history to start with. We are an Ethereum team, proudly speaking at Bitcoin Plus Plus right now. We did a lot of indexing work and spent more than 7 years in the Ethereum realms until the ordinals happened. I myself dealt with a lot of Bitcoin stuff back then, moved on to Ethereum, now building on Bitcoin one more time. We didn't build much back then. There wasn't many things to build on. That's why we loved ordinals, because it showed a way to building applications on top of Bitcoin in a permissionless way. So it started with images, but then what it evolved into is the BRC20s. And to go quickly, this is our bestinslot.xyz. This is one of our products. It uses our like indexer, and it's like a consumer application, fully Bitcoin native consumer application. So these are all BRC20 tokens, and then like we have all these data and services going on with the indexers, which I'm going to talk briefly in a couple minutes. But basically, this is BRC20. Okay, it's an inscription. It's literally a text data written onto Bitcoin. All these metaprotocols, basically, we write data onto Bitcoin. Bitcoin handles the ordering, basically, and then we have these so-called indexers that looks at the Bitcoin blockchain, the data, it's already ordered there, and it makes meaning of that data. There has been more than 50 meta protocols so far since ordinals began, but like majorly people know about ordinals, runes, and BRC20 so far, and now like BRC 2.0 is just getting started. So moving on, we close this. So this is BRC20. And again, 2.0 is, we're literally upgrading BRC20 as the lead maintainers. So the goal is to make it programmable directly on Bitcoin layer 1, to have applications on Bitcoin layer 1 utilizing this on-chain data, off-chain indexer approach that ordinals introduced. So I'm going to talk a little bit about indexers because like it's a Bitcoin plus plus at the end of the day. So OPI is right now the industry standard indexer for BRC20 and BRC 2.0, but many teams also use it for ordinals and runes as well. It's a generalized indexer for meta protocols on Bitcoin. heavily optimized for BRC20 and BRC 2.0 at this point. You're welcome to check it out on GitHub. We also have a light client. This is one good thing about this is that like any average developer can just download OPI and start running it on their laptops. So one thing with ordinals, runes, BRC20 is that like, hey, what about the indexer? Like that's the only kind of argumentative medium for all these like Bitcoin meta protocols. But the point is that since the data is already publicly available and ordered, then when you have a canonical indexer, and like Ordinals has a canonical indexer, BRC20 has OPI as the canonical indexer, it's like, hey, you're welcome to build your own indexer and run it your way, but make sure your solutions match the canonical one. So instead of in the Ethereum world, we have this like spec sheet and all different kinds of like clients. In the Bitcoin world, these meta protocols works in this like canonical indexer approach, which is quite simple and effective, to be honest. Like, so what BRC 2.0 does? So, it went live on on Monday around 2 p.m. So it's been around like 2 days since it went live, and it's been the craziest 2 days of our lives so far. Discord is melting down right now. Anyways, but what 2.0 does is essentially enhances the indexer with an EVM. When you think about it, like ordinals, BRC20 runes, these indexers are similar to calculators. All they do is like additions and subtractions. They don't do much more complex things. Very simple, like literally simple calculator applications. BRC 2.0 basically take this concept and take this fully into the Turing completeness realm. You're leveraging EVM in the indexer. When I say EVM, this is not Ethereum, it's just the execution engine. There are like specific reasons we chose, but there is no validation between indexers. There is no nodes with staking tokens confirming the state because it's already handled on the Bitcoin blockchain itself. So, and analogically speaking, like now these meta protocols are moving into their like next stage in their life, which are like laptops, like fully computers. And why we chose EVM? I mean, there are like many reasons. My practical reason is that like we want apps on Bitcoin tomorrow, not another 3 years later. So we took EVM because it's super easy to build with. My co-founder is extremely well knowledgeable with EVM and all Ethereum stuff. There are thousands of battle-tested smart contracts already ready to use. And we want to be interoperable with the rest of the Web3 world as well. And there's a huge developer community. Like EVM developer community is huge, and we see BRC 2.0 as a way to make it more attractive. We are also going and talking at Ethereum events. For example, on Friday, we have a talk about this at an Ethereum event in Istanbul. So we already see quite demand from teams. Like there are a couple teams that we're going to launch products on Base that are like getting in touch with us. They're like, hey, we want to do it on Bitcoin because it's open, blue ocean, and a lot of entrepreneurs see this as a opportunity. It's an opportunity right now. Like it literally launched Monday. I mean, it's been on testnet for 6 months. There are like many more applications that are coming up. But yeah. So yeah, we basically took Ethereum, like if Ethereum is a car, we took the engine and we put it in the indexer to make it extremely simple. There are a lot of puzzle pieces to make it work with Bitcoin wallets and like Bitcoin signatures and stuff, but it's basically it. So I'm gonna move on. So this is the Explorer. This is an Explorer anybody can build using OPI. This is literally like an Ethereum or like Arbitrum, whatever EVM chain you wanna look into. It's an Explorer. It's like a EVM Explorer. And since Monday, we have like, 3,006 transactions. It's like average block time is kind of funny because it's Bitcoin block time. It's around like 7, 8. This is average since this has been running. And yeah, we launched on Monday and it's been like going up. There has been many hiccups, but it's working. Like right now, it's working. So I'm gonna show a little bit about, this is the Signet one, the mainnet one. We didn't have time to make it online, but this is basically like an interact deploy interface. You can deploy smart contracts. These are literally Solidity or Viper or whatever Ethereum tool you wanna use. Majority of them works out of the box with BRC 2.0, but some applications needs more sophisticated approaches. Like an EVM developer can easily build on top of BRC 2.0, but if you both know EVM and Bitcoin, then when you can build very more sophisticated consumer applications or like applications in general, dApps on Bitcoin. So, okay. So, and then like, these are like contracts that you can interact. I'm gonna go, this is like a simple contract. You can say, okay, like get value, okay, like 420. You can write to it, you know, it's, say like 99, or like, let's say 21 million. Anyways, I'm not gonna lose much time. Whoopa, full screen. Your Unisat wallet opens, or like Xverse, whatever Bitcoin wallet you're using. These are all happening on like layer 1. You sign, and then transaction in progress. And then this is like a simple transaction. What it actually is, it's an inscription written, it's a command written on the Bitcoin blockchain, and then the indexer making sense of it, and then the applications making even more sense of it for users to use this thing. And then it's not mined, so it's not gonna update, but it's supposed to like here, you know, like we want confirmation things. So this is live. I'm gonna show you some live stuff happening right now. Another application. This is again best in slot. You can see all the BRC 2.0 tokens. These are like BRC 2.0 tokens is actually kind of like the first BRC 20 tokens that can exist in both metaprotocols, because BRC 20 is huge. Like there's Binance, there's OKX, our business partners Unisat. Like there's a lot of big players in the BRC 20, and because it's like a super distributed meta protocol at this point, we split the BRC 2.0 upgrade into 2 phases. Phase 1 happened on Monday, and it basically opens the 6 ticker, like a new 6-byte ticker domain name for tickers. So these are the first programmable tokens. You can have them in BRC 20, or you can have them in BRC 2.0 as well. It's like analogically speaking, it's like Ethereum, like ETH and WETH. You know, you can wrap and unwrap ETH. It's analogically super similar. So this is live. This is mainnet. These are like this. This is one of the tokens, like Acorns. We helped them do the airdrop. We did the airdrop yesterday to 6,000 wallets on Bitcoin, and we spent $50. It's a extremely efficient way to do things on Bitcoin as well, because once you have this text command, like here, like this is another inscription. This is the, which one was this? Anyways, doesn't matter. This is the buy one. This is the buy one. This is a buy inscription, okay? This, sorry. Oh. So this, it's literally like compressed commands happening on the Bitcoin, but this looks like one transaction on the Bitcoin blockchain, like on mempool, you see, you know, like 4,000 transactions in the last block, etc. So this is just one transaction, but what it does is executes a command in the BRC 2.0 indexer, which actually does multiple things, and it turns out to become like an airdrop for 6,000 different wallets. So right now, okay, like there's like 5,000 something now. Some people sold their airdrops, looks like. So this is our DEX. This is the first DEX for BRC 2.0. And this is fully smart contract powered. This is trustless and decentralized that uses this BRC 2.0 logic. This is only one of the very first applications. And it has a lot of ways to go still. But I'm going to do a live buy right now. Okay, let's go. My mainnet. I'm gonna dox. Let's get doxed, sir. It is not. Okay, this is this one. Anyways, so I don't know if you traded ordinals, runes, or BRC20, but like the trading experience is like very cumbersome. So with smart contracts, now this opens the door to all kinds of applications. And one thing that excites me personally a lot is also like sequencers and new breeds of layer 2s using like rollups and stuff through this BRC 2.0 meta protocol. But that's another topic. So we go like, okay, buy 500. Oh, more. Let's buy 5,000. And then you sign, okay, like it requires 4 signatures. What this does is basically what it does, the 4 signatures.
So the first transaction actually sends the BTC to a holder wallet, handler wallet, and then the second transaction is a ordinance commit transaction, which creates the wallet for the ordinance to be created. Third transaction is the reveal transaction that actually creates the inscription. And the fourth one sends this inscription to an op return to activate it and burn it, which actually solves the UTXO bloat issue that came with BRC20. The inscription also has the details of the payment transaction, so the smart contract can actually verify the payment transaction sent the exact amount, and it has the enough BTC for the buy, and also it checks the sell orders if they have enough tokens or not, and then just fulfills them.
So we launched this around 24 hours ago, already settled around like $200,000 of volume. Luckily, nobody lost money. There has been some bugs and hiccups, but we've been fixing all of those. Yeah. So yeah, right now the transaction is broadcasted. So this is an order book approach. This is the very version 1. But it's also like a way to showcase what's possible now. We're going to introduce like instant trade execution, like swaps, like those kind of stuff are like coming. We have a long way to go, but this is Bitcoin DeFi, real, in action, working, went live on Monday. So moving forward, so this should be the buy transaction. Yeah. Yes. So this is normally like a EVM code. This is like a solid function call, but we also use a compression to take less V bytes on the Bitcoin blockchain, basically. But technically, we can literally write the code here as well for nerdy visuals on Bitcoin blockchain. People like that stuff. And then, yeah, so for example, this is another beautiful transaction. This is a buy transaction. What happens here is that, again, like a function call happens, it calls a bunch of other things, and then at the end of the day, one single buy order fills multiple sell orders. These are like pretty standard and very common things in Ethereum, Solana, like those chains right now. But this brings the best of both worlds. It's like now you have EVM with Bitcoin security. So, and especially if you know how to like handle UTXOs and like some Bitcoin development on top of EVM development, you can do stuff like this. So it's a new way to build stuff on Bitcoin. Yeah, so we can go more into details. Like this is the, you want to explain a little bit?
This is the airdrop contract. So, where is it? Sorry. So this contract actually distribution contract. You can have vesting schedules. You can have claim using Merkle root, and also you can airdrop via an extremely simple function right here. And this is the airdrop command that we run, which airdropped 6,000, which airdropped to 6,000 wallets, and which took like $50 fee, miner fee.
1 sat per vbyte. So if it goes more, it goes more. Yeah. Yeah. So. Okay.
And also, every block has 51 billion gas. And also every vbyte has 20K bytes. So if anyone wants to do a DDoS attack, they need to fill a lot of Bitcoin blocks, which is extremely expensive. And even if they do that, we can index them in 15 seconds. So DDoS is solved by this approach. And also we use compression, so we also took precautions about zip bombs as well.
So additionally, some comparisons between this approach is interesting emergent properties we discovered along the way when we were working on this protocol, which is like, for example, on Ethereum, you need to complete indexing under 1 second.
Yeah.
Like around like
blocks are 12 seconds.
Yeah, blocks are 12 seconds, so you need to complete the indexing in 1 second, so you have time for nodes to speak to each other, shake hands, etc. Because with metaprotocol indexer approach, there is no validation, plus Bitcoin block time is around 10 minutes, we can have, instead of 1 second indexing, we can have 20-second indexing. We set it to 15. Yeah, like right now we set it, the indexing time, to 15 seconds. So what happens is when you need to index things in 1 second, that's where the gas limit comes from on the Ethereum world. Because like if you have a lot of like complex things to be executed, you can't complete the indexing in time. Therefore, you need a gas limit. With 15-second indexing time, you can have much higher gas limit. So what this means is that in 10 minutes, not block time, in human 10 minutes, on Ethereum, through BRC 2.0 approach, you can have 40 to 50 times more computation than 10 minutes of Ethereum, like multiple blocks, than 10 minutes of Ethereum. Yeah. So about the indexing, like before we started building on Bitcoin, we spent around 8 months to build a indexer for all EVM chains, ready for the future of billions of NFT transactions, billions of DeFi transactions. So we did quite a lot of things regarding to indexers, and it's like a quite critical topic in the blockchain world. So yeah, this kind of excites us because people can say, oh, it's expensive to do applications on Bitcoin, but because of this huge gas limit perk, it can actually be cheaper even in many circumstances. I'm not saying it's going to be like cheaper than Ethereum at all the times, but there are quite a lot of cases where it can be cheaper. For example, the airdrop. Yeah. Because you pay per vbyte for a simple command. You don't pay for the whole computation. So it doesn't, some things doesn't, everything scales with complexity, but not drastically. So some things that is hard to do on Ethereum is actually kind of easier to do on BRC 2.0 Bitcoin. So yeah, we can have we have any questions, anybody wanna hey, this doesn't make sense, or like, stop spamming Bitcoin blockchain, please.
Thanks. Look, sounds actually quite nice. So you're saying the bloat is gone.
Yeah.
And how is about reuse about, let's say, BRC 5 byte? And why did you decide to name it after BRC instead of RINs?
Okay.
So the system actually works very similar to BRC20. So that's why we made it an upgrade to BRC20.
One addition. We are the guys who maintain BRC20.
Yeah.
Like, we've been writing the indexing rules. We've been writing all the documentation for BRC20. We did a lot of things for BRC20. Like, it works. Like, everybody uses the OPI. We wrote the indexer. So right now, governance-wise, there is a dual maintainership with us, Best in Slot, and Unisat. So we are the maintainers of the protocol, and we are upgrading BRC20 because we can. Like, we are the maintainers of it. So it's not like BRC 2.0 is not a standalone Neve meta protocol. It is a standalone meta protocol. It can function without touching BRC20, but it's built in a way that it's backwards compatible, and BRC20 can move in and out of this meta protocol.
So if we wanted to do this on runes, we had to work with Casey and also upgrade Ord. So, yeah. About the other thing, the 5-letter tickers, these will be opened on phase 2. We are currently working with Unisat, OKX, etc. to make all of the indexers synced. When everyone is synced, we will allow the other tickers as well.
Yeah, sync is it's not a technical thing. It's more like a, hey, are you ready? Unisat is ready. Yeah. OKX is taking a little bit more time, but like, we're helping them to do it. Yeah. So before I forget, we are releasing BRC20.build this week. It's like,
sorry, docs.
Okay, down. Sorry.
Yeah.
Or like, why?
That's back.
No?
It's not about that.
No, not about that. No. Anyways, BRC20.build. We're going to have extensive documentation here. Why is it not working? You don't know? Okay. Okay. So we have a lot of examples on how to build applications. Everything is open source. We keep publishing new open source documentation as well. The thing is yes, we do want more Bitcoin people and Bitcoin developers to come build applications with BRC 2.0. But I'm going to be honest, there is a huge ocean of developers in the broader Web3 world. That's why we're also focused on bringing EVM folks to come build on Bitcoin as well. So that's another one of the goals, because it's programmable money. It's a Bitcoin dream. It started on the Bitcoin. That has been always the dream. All the DAOs and different kinds of applications, those started in Bitcoin communities, and then all the developers moved on to other chains because we couldn't build on it. Fast forward 15 years almost, 14, 13, whatever. Now we can build stuff on Bitcoin. So I invite everyone to ask questions. If you want to build something, we're helping a lot of teams. We would love to help if you want to build some stuff. Thank you.
In just a couple of moments, we're going to have Dominic Hartz from Bob joining us here on the main stage.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025.
Ladies and gentlemen, continuing the main stage content here at Bitcoin Plus Plus Scaling Edition, Dominic Hartz from Bob. Please give a very warm welcome. Thank you.
All right. Hello and welcome, everyone. My name's Dom. I'm from the Bob team. I'm going to talk about what we're doing, which is the gateway to Bitcoin DeFi. And there's three main things I'm going to talk about, like how we're connecting Bitcoin to Ethereum. Why do we want to do that in the first place? How are we going to do that? And what does this really have to do with Bitcoin? How do we get Bitcoin security? Also, apologies, they sent the Ethereum guy to a Bitcoin conference. So if I talk a lot about of EVM stuff, just roast me in the questions after the talk. All right, cool. So why are we here? Like very high level, and this is a little bit marketing-ish slides. So Bitcoin is just bigger than everything else combined. Like if you look at Ethereum, Solana, the two second largest ecosystems, Bitcoin is just so much bigger. But if you look at like on-chain, TVL, DeFi, then you have about 30% of Ethereum's. 30% of Ethereum is basically on-chain DeFi, TVL, and in Bitcoin, if you look at the on-chain DeFi, it's only 0.3%. So there's like, if we scale, all us collectively as we're scaling Bitcoin and getting some use cases, real-world use cases are cool, then there's like 100x opportunity if you do some napkin math, basically. But if you look at Bitcoin on-chain today, most of this is actually happening not really on Bitcoin. Like the majority of Bitcoin that's being used on-chain is used a lot on Ethereum, on BNB, which all have nothing to do with Bitcoin security. So there's just a lot of Bitcoin flowing around, and there's also like growing interest. So this is like CBBTC mining, quite centralized, and the Morpho, which is a lending protocol on Base. Supply that's going up. So there's a lot of kind of interest. So you have a whole bunch of users that actively use Bitcoin on chain, but they're not necessarily on Bitcoin. And also one trend that I like to kind of point out, when you go to DeFi today, like it's very different from like 4 years ago when we had DeFi summer. Like the DeFi apps have come kind of a long way. You have now like these social sign-ins, for example. You don't, as a normal user, you don't really have to bother that much with seed phrases anymore. If you don't want to, you can still do it. You have big markets. So Aave, for example, here that I took as an example, like these supply and borrow rates, like Aave has like $40 billion in assets on chain, so this like huge. So they're like relatively stable as well. And you can even have like cool stuff with zero knowledge proven P2P on-ramps between like Revolut and Venmo to like USDC right away. So there's like a lot of cool stuff happening in the like EVM side of things. And apologies, this was my Ethereum plug here. But okay, where do we start? Like we have a lot of opportunities right now. So institutions looking for Bitcoin DeFi yield. There's a lot of apps that we are talking to. They're looking for adding Bitcoin into their DeFi. There's pretty much all the major chains looking for some sort of DeFi strategy, and we think that within the next 12 months, like this will just continue to grow because Bitcoin clearly has a unique market position. But there's a lot of problems, like if you look at Bitcoin DeFi today, usually if you want to on-ramp to DeFi, there's a lot of transactions required. Bitcoin has come kind of a long way with wallet support in the last few years, but it's still kind of complicated. There's a lot of new protocols popping up, which tend to be risky. There's obviously no native yield on Bitcoin. There's a lot of centralized wrappers, so why bother using CBBTC or WrapBTC if I can just go to Coinbase directly? It's just almost the same risk, I'm assuming. And there's a lot of fragmentation like across chains, and yeah. So I guess there's a lot of technical talks already on like BitVM and stuff like, but I want to kind of focus on what we see as like the package. How do we actually get more people to use Bitcoin, which I think is a beneficial goal for us all. So we have a kind of two-step approach. So our first idea is, well, there's already a lot of chains and a lot of DeFi apps that want access to Bitcoin. So these are our very clear first candidate is like, get everybody who wants access to Bitcoin, give them access to Bitcoin with the least resistance possible, like one single Bitcoin transaction. And if they want to exit back to Bitcoin, also make that a single transaction, and then build out like a proper Bitcoin DeFi ecosystem on the Bob chain, which is then secured and finalized by Bitcoin. And this is where I'm going to talk a little bit about the hybrid L2 design. So this is also the rest of my talk is going to be really focused on the first part, multi-chain Bitcoin access, and then the second part is the hybrid L2 native Bitcoin DeFi. All right, so gateway. Bob Gateway is what we call multi-chain Bitcoin access. It's basically from Bitcoin in a single transaction to any asset on any chain to any app that you want, or the way back from any asset, from any app, from any chain back to Bitcoin. The way that we're basically building this is we specialize on the Bitcoin to Bob way. This is an intent-based bridge. And then we partner with third-party bridge providers like 1inch, Across, Layer 0, Chainlink to bring existing Bitcoin wrappers like WrapBTC, CBBTC to other chains, and then get that into the different apps and then have it in your wallet. And the whole, like basically this whole journey, say from Bitcoin all the way on the left to like into your apps and your wallet, this is just a single Bitcoin transaction. On the way back, it's also just a single EVM transaction, or, well, there's a single Bitcoin transaction involved as well, but the user doesn't have to do that. There's large parts of Gateway already live, so you can basically try this out, mostly on Bob right now, so you can like put your Bitcoin into Xsolve BTC, which is the Babylon staked version. Yeah, you can try this out if you want to after this talk, and Bitcoin swaps are coming soon as well. Since this is a bit of more of a technical conference, I want to go a little bit into the technical details on that. So Gateway is there's a front end to it, but the main use case we actually see is a SDK, so people can use it. It's programmable, and it's relatively simple. You basically have to do 2 API calls. You get a quote, essentially, where you say, I want to go from, say, Bitcoin to Base or to Bob, and I want to go to this user address, and there's a certain strategy that I might want to do. If you want to do certain strategies, the call looks a bit different, but basically the get quote looks exactly the same. And then what like a relayer will return to you is like how to construct the transaction, and then you do your second SDK method call here, and you get a transaction ID from that that you can then submit to Bitcoin. Sorry, actually this is submitted on your behalf. You just sign it in between. So from Bitcoin, it's super simple. You construct a Bitcoin transaction that has 2 outputs. One is like a amount and a recipient, which is usually a solver on one side, and then op return to identify what exactly you're trying to do. And how this kind of looks like. So we have, in the middle, there's like 3 parties involved. So you have users, you have relayers, and you have solvers. Intent-based bridges they kind of mix all of these names. But for our purposes, we're going to use relayers and solvers here. Relayers being the ones that relay the information of the users, solvers, sometimes called LPs or market makers. They basically supply capital and swap it with the user. What the user does is I'm submitting my intent. So let's say I want to go from Bitcoin to I want to supply CBBTC into Aave and then take a USDC stablecoin loan against my WrapBTC. This is like basically the EVM transaction is I go WrapBTC on Bob, I go from Bob via say the layer 0 bridge to Base, then I swap it in a DEX pool, and then I supply it into Aave, and then I take out the loan. And we can encode this entire EVM call data, also all of these calls basically, into like one transaction, and then we hash it, and then we put it in the op return. What the relayer does is it registers this intent, and then like the solvers basically say, cool, I'm giving you this quote to execute all of these actions. And then what the well, the solver would also deploy the necessary liquidity, so the wrap BTC on the Bob side. The user then can check on the Bob side, okay, the solver actually put the liquidity there, so my risk is very low because the solver can't actually withdraw the liquidity right away, like there's a time lock on this. Then the user sends the Bitcoin, puts in the operator the hash of all of these actions, and then we are executing this via Bitcoin Lite client on the Bob side, and with that you basically just went from Bitcoin to like borrowing some stable coins on Base. That's kind of the magic there. And then on the way back, I think the interesting architectural thing here is it's pretty much the same. Like on the way back, like user registered their intent, says I want to go from, I don't know, I have wrap BTC on Avalanche and I want out back to Bitcoin, and then registers the intent, relay that to the solver. Solvers reserve the Bitcoin. User locks the wrap BTC, and solvers then executes the Bitcoin transaction. The interesting part about how this protocol is constructed is that we always lock and verify funds on the EVM side. That is because that's just a lot cheaper than if you try to do any locks on Bitcoin, as you probably all know quite well. So on Bitcoin, we always just have a very regular transfer with an op return, and on the EVM side, we handle all the complexity of locking. So Gateway's live. It's super efficient in terms of like cross-chain swaps because, well, again, no hash locks, no time locks, no nothing, just a regular Bitcoin transfer. All of the security part is handled on the EVM side. You have a Bitcoin Lite client that is kind of the main security component. So basically, Bobchain tracks all the Bitcoin headers. It's live on mainnet, so you can try it out if you want to. And so with Gateway, we can basically go from Bitcoin to any chain and back. And now the question is like the long-term vision obviously is that we want to have a native like Bitcoin ecosystem. And for that, we actually need to have something that's also secured by Bitcoin, because clearly any Bitcoin DeFi on Base or Avalanche or any other chain isn't actually secured by Bitcoin. Like the security depends on the wrapper and the consensus of that chain. And with like how we do the Bob L2 basically, that's how we can get to Bitcoin security. So very, very high level. We use Bitcoin as a finality anchor. So Bob will be committing state proposals basically to Bitcoin. We use ZK proofs for security. That is already live on the Ethereum side. We use BitVM for bridging, and then we use the ETH native bridge to get stablecoin access, to get access to all sorts of other assets. The idea is you always checkpoint first to Bitcoin, and then you treat Ethereum. If you think about client-side verification, you commit to Bitcoin. Bitcoin cannot verify that your commitment is actually correct. You treat everyone else like as a client, and Ethereum is a very expensive client that validates whatever is actually on Bitcoin. So you essentially go ahead and say, oh, I need to submit my state proposal to Ethereum now to settle the bridge there, but I also need to give it a Bitcoin-like client proof that this commitment was actually made on Bitcoin first. And then kind of where we are right now, we have phase 1 is completed. So Bob launched initially as a pure Ethereum rollup. So we use Ethereum SDA. We have now ZK fault proofs on Ethereum. They're live. So you get the full Ethereum security, which means we get one transaction on Ethereum to proof any kind of fault. We have this interesting thing called on-demand validity proofs. So because our fault proofs are in ZK, we already do the ZK proofs of our Bob blocks, and we can, if there's demand, submit a validity proof to speed up withdrawals from Bob. And we have Bob Gateway being live, so you can do this one one transaction on an off-ramp to Bitcoin. What we're working on right now is this commitments to Bitcoin. So checkpoint all of the Bob state to Bitcoin, and then check on Ethereum that Bob was checkpointed to Bitcoin first, and include that in the fraud proof / validity proving mechanism. And with that, also on the BitVM side, where we're working on the BitVM bridge, make sure that we have the commitments there. And then, well, long term, what would be really nice is to get full Bitcoin security. I'm kind of going to skip over this. So I think there's a few kind of approaches that one can take. BitVM fault proofs for full state verification, but you would kind of need to have all your transaction data on Bitcoin, which doesn't really scale very well right now, or you need to find some other clever way around DA. This is very much a R&D kind of project. So to kind of wrap it up, so if we have Bitcoin finality on Bob, and we can use the ZK verification on both the BitVM bridge and on the Ethereum side for the Ethereum bridge, then we can kind of build Bitcoin secured interoperability, because it's so easy to verify Bitcoin on other chains that you could also think about like connecting all of these other chains basically via like client proofs. Yeah, and Bitcoin security everywhere. Yay. Cool. So to wrap it all up, so we have Bob is like based on a P stack, uses the EVM, has a native ETH bridge. You get all the rollup security from ZK proofs, from ZK verification. You get Bitcoin finality from the checkpointing. We're building out the native Bitcoin bridge via BitVM, and then you have Bitcoin intents like one transaction, onboarding, offboarding via Bob Gateway. And yeah, I'm gonna open it up for questions. Thank you. Are there any questions? Yeah, there's one question in the back.
Test. So by checkpointing on Bitcoin, so the Bob will inscript the state root on Bitcoin, right? Or doing any other stuff?
Yeah, so basically, yes, you inscribe the, well, you would likely put it in operator, not use the ordinal type trick for inscriptions, but because it's just a state root, the 80 bytes from the operator is typically enough for us.
Okay, thanks.
Cool. Any more questions? No? Awesome, cool. If you have more questions or afterwards, like, feel free to ping me, Telegram, Twitter.
An ancient city. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025.
Cool. Shall we start? All right. So today I'm going to talk about a new thing that we came out with called Trustless Bitcoin Vote. And I figure since every other talk here is about BitVM3, I last minute added the title BitVM3 in desperate effort of attracting a bigger audience. All right. Okay. So what's the problem we're trying to solve? Okay. So Bitcoin is the beginning of the whole thing, all right? So Nakamoto tried to build an application, the first application, decentralized application, payment on this Bitcoin. Since then, Bitcoin became something else. It became a store of value, now more than $2 trillion. In terms of applications, most of the new applications happen not on Bitcoin, but elsewhere. So smart contracts on other chains which have much better programmability than Bitcoin. Okay? So we are in a strange situation. We have an asset worth more than $2 trillion on the left, 60%, 70% of the crypto economy. Yet the interesting applications are all on the right-hand side. So the natural question, and I think is a problem that a lot of people are trying to solve, is how do you bring these Bitcoin into these smart contracts so that you have more activity? So that's the problem that a lot of people are trying to solve. And the standard approach is through bridges. So currently there are two main bridges from Bitcoin to the smart contract world. One is called WBTC, the other is called Coinbase BTC, CBBTC. In total, they are less than 1% of the total Bitcoin supply. So you can see that, first of all, very interestingly, both of these bridges are centralized, basically run by companies. And two is that very, very little Bitcoin is actually bridged through them, little compared to the total supply of Bitcoin. Okay? So this is not a very desirable situation. Okay? So what you want to see is you want a lot of connectivity between Bitcoin and these smart contracts so that the economy can be more thriving. And so ongoing work, there's a lot of work, many talks in this conference to build Bitcoin bridges, better Bitcoin bridges, less centralized, less trust to connect the two worlds. And so this is an example of such an effort, BitVM2 bridge. So we just put this paper on preprint a few months ago. And in that paper, we did a careful analysis of the trust assumptions. Okay, so one thing about protocols is that we need to understand the security of protocols. Security of protocols means what kind of trust do you need to make in order for a protocol to satisfy a certain property. Typically, the properties are in terms of liveness and safety. Okay, so here you can see that there are several important properties here. For example, peg-in liveness means that you should be able to peg into the bridge live. Peg-out safety means that when you try to peg out, you should be able to get the money if it belongs to you and not lose the money. So you can see that while the BitVM bridge is better than a standard multi-sig bridge in terms of the trust assumption, it is still trusted. Okay? You still have to trust a set of committees called signers and a set of operators. And you can see actually the trust assumption in some cases are quite strong. For example, to achieve 1 out of n signers. So you often hear that BitVM bridge have this 1 out of n security, better than majority assumption for multi-sig bridge. However, to get peg-in liveness, you need n out of n signers. And in practice, it's kind of hard to get this n out of n. So there will be some trade-off in a realistic implementation of a bridge between this number and this number. But the high-level picture is that even the best bridges that we have so far have some trust assumption. So they're not, see, even the baby doesn't like bridges with trust assumption, so she's complaining. All right. So we don't really get trustless bridge. We get trust, okay, people advertise themselves as trust minimizing bridge, but what does that mean? So in this paper, we don't use that word, trust minimizing bridge. So we just say that this bridge is actually a light client-based bridge. So anyway, so you may say, hey, these trust assumptions, maybe it's because we're using BitVM2 and not BitVM3. Hey, come on, David, catch up to the time. Everyone is now talking about BitVM3. Nobody's talking about BitVM2 anymore. You're behind the time. Maybe with BitVM3 can get rid of all these trust assumptions. No. Answer is no, okay? Even with BitVM3, you get exactly the same set of trust assumption, actually. So if you remember what Robin said in the first talk of the afternoon, Robin said that in a bridge, there are two parts, okay? One is there is the protocol, which is run by a set of pre-signed transactions, okay? And two is there is the verifier. There's the verifier. So BitVM3 is an improvement on the verifier. But the protocol, the transactions are still limited by what? By the lack of covenant, okay? So all these trust assumption is because of some form of lack of some form of covenants. Okay, so how do we improve the situation? So the observation here is the following, okay? Bridging is a means, not a goal. The goal is to allow Bitcoin to hopefully, trustlessly participate in DeFi, okay? Right? So bridging is one way, but it's not the only way. All right. So in fact, the motivation for this point of view, this bridging-less point of view, is from a protocol that we have developed, we as in the Babylon project, for which I worked in. So Bitcoin staking. Okay, so what is Bitcoin staking? So staking is actually probably the most basic DeFi primitive. Okay, all right. So you take your asset and you provide as a collateral to provide security to proof of stake system. So Bitcoin staking is basically a way for a Bitcoin holder to use their Bitcoin, okay, to secure proof of stake chains, okay, proof of stake chains, and that's the protocol we built. Now, the naive solutions problem is, well, okay, let's wrap those Bitcoin, CBBTC, WBTC, wrap it over Ethereum, some other proof of stake chain, and then use that as a staking asset. Okay, but then you have to go through this trusted bridge. So what we achieved in this protocol is to do this without bridging, and therefore achieve the trustlessness of the protocol. Okay, so you can see one of the main advantage of not looking at it from a bridging point of view is to be able to do it trustlessly. Okay, so this is the protocol. To give some evidence of the value of building such a product, trustless product, is that it is actually I believe this is actually the largest native protocol on Bitcoin, largest by TVL, by total value lock. As of a few days ago, I never know whether it changed for a few days, but last time I checked, it was 56,000 Bitcoin, so more than 6 billion Bitcoin staked on this protocol. This is probably the largest. Now, so you can see the value of having a protocol that is trustless. Bitcoiners don't like trust. Okay? All right. Now, so I want to use this example of this protocol, which is no bridging protocol, to introduce this concept, which I want to advocate as an alternative to bridges in a more general way, okay? Which I call a trustless vote, okay? So I'm going to use this trustless vote to think about the staking protocol that we've developed, okay? How does it work? A staker shows up, okay? One of those, we have about 200,000 stakers right now staking on this protocol. One of those stakers showed up. He or she deposits a Bitcoin, onto a vault. Okay, what is a vault? Vault is nothing but a UTXO. The UTXO is locked, okay, with certain unlocking conditions, okay? And there are two conditions for this application. One is that the staker can unstake, okay? That means the staker can say, oh, I don't want to provide security anymore. I want to take my Bitcoin and go, okay? And two is slashing, okay? So slashing basically means that the staker is delegating the stake to some validator on another blockchain, okay? And something happened, and that something happened will activate the slashing path, okay? So that's how this protocol is designed. And it's trustless in the sense that the staker can always unstake, provided that it doesn't get slashed, okay? And slashing is an action that is controlled by the staker, or most precisely, controlled by the validator that the staker delegates on. So that's why it's a trustless protocol. Okay, good. Now, so we invented this Bitcoin staking protocol about, I don't know, 2 years ago? Yeah, about 2 years ago, 2.5 years ago. And one of the questions we ask, okay, is if you look at the structure, right, one can try to think about generalizing the structure, okay? And the generalization is maybe it's not sticking anymore, okay? But in any case, it's a specific application, okay? A specific application. And in that application, you need Bitcoin as some form of collateral, because that's what staking is, collateral. And under some conditions, this collateral can be withdrawn by the depositor himself. Under other conditions, some kind of slashing conditions, the collateral is now going on a different path, okay? So let us test whether this idea can be generalized and what difficulty we face as we try to generalize it. Okay, all right. So a very natural, actually, application is lending, okay? So you have your Bitcoin, okay, and the store value, so sitting there, nothing to do. However, you need some USDC, you need some fiat to, I don't know, buy mining equipment, buy a house, buy a car, do something with it. You don't want to sell your Bitcoin, so what do? You use the Bitcoin to borrow some fiat or stable so that you can do things with it, okay? So it's a very natural application because Bitcoin is something that people do not really want to sell. Just like a house you don't want to sell, you mortgage the house in order to borrow some money, okay? All right, so you can draw a very similar picture actually than the staking picture with the staking picture. And suppose we have two characters here, okay? Bob, the borrower, and Larry, the lender, okay? So Bob has Bitcoin, Larry has USDC, okay? So Bob deposits some Bitcoin into this vault, which acts as a collateral for which Bob borrows some money from Larry, okay? And this borrowing money from Larry is USDC, so sitting on some other chain, maybe Ethereum, okay? Example, Ethereum. All right? So now this vault have two exit conditions, okay? One by Bob and one by Larry, okay? So if the loan is repaid and the Bitcoin price remains above a certain threshold, called liquidation threshold, in this example, 50K, then Bob can redeem the Bitcoin from this vault, okay? In other words, Bob can leave and take out his collateral, okay? On the other hand, if the Bitcoin price is below 50K, so liquidation threshold has been triggered, then Larry can go and liquidate this vault, okay? So this is the desired goal, okay? All right, so now I want to build a protocol around this picture so that we can do this trustlessly, okay? Trustlessly means what, right? If you think about it, there are two characters here, Bob and Larry. So trustlessly means that Bob doesn't need to trust Larry and still be able to achieve his goal. And Larry doesn't need to trust Bob and Larry can still achieve his goal. That's what trustlessly means in this example, okay? So to achieve this, we need to specify a protocol. And this protocol has two parts to it, okay? One, you need to be able to specify these withdrawal conditions that I write down, okay? That defines the vault. So that's the first one. Withdrawal conditions should be able to specify using Bitcoin transactions in a trustless fashion, okay? I'll make clear what that means, okay? Second is that when these withdrawal conditions actually happen on Ethereum, okay, they should be verifiable on Bitcoin trustlessly, okay? So if you achieve both goals, then the whole thing is trustless, okay? All right, so let's break it down. All right, so in the first one, okay, you need to sign a bunch of transactions, pre-sign a bunch of transactions, so that the protocol will follow these transactions. Now, if there were covenant, then you don't need to pre-sign, okay? However, there's no covenant. So here, effectively, we are using Bob and Larry as the covenant committee, okay? And they are jointly pre-signing a set of transactions. Now, I claim that these rules, these conditions, are specified in a trustless fashion because because these are the rules, okay? And none of Bob and Larry can change the rules by themselves, okay? By himself, let's say, without, by himself. So therefore, you don't have to trust the other party. You need both in order to sign a total set of transactions. So here the rules are trustlessly specified, okay? Now, actually, this part is the advantage of this structure over a bridge. Because you see that because this vault is tied to this application, the folks that are signing on the vault are also the folks that are interested in this application, Okay? So that makes the possibility of achieving trustlessness even without covenant. Okay? All right. Now, the second part is the verification part. Okay? Now, how do you verify stuff on Bitcoin? Okay? So if you look at the history of Bitcoin protocols, okay, starting with basic protocols like atomic swap, Lightning, okay, all of them uses basically one trick, okay? And this trick is called hash time lock contract, HTLC, okay? So basically the structure of HTLC has two forms, okay? Basically, the one form is that Bob tries to make a claim, okay, and then to make the claim, Bob has to somehow reveal a secret that they can decrypt, okay? And within a certain time, if the secret is not revealed, then the timeout, and then the claim will fail, okay? So this is a non-challenge-based HTLC, okay? For example, atomic swap have the structure. Now, there's also a challenge-based version of HTLC, okay? Now, in this challenge-based version, Bob is trying to make a claim, but Larry is the challenger, and Larry is trying to stop Bob from claiming if Bob's condition of claiming is not met, okay? So then Larry will go and reveal, extract, and decrypt a secret S, and using that secret, it can stop Bob from claiming. And again, within a timeout, if this doesn't happen, then the claim will succeed, okay? So you can see these two pictures. One is non-challenge based, one is challenge based. But both are based on idea of extracting secret. A good example of challenge based is Lightning, okay? If someone finds that the state is more updated than the state that is reported by a claimer, then it can extract a secret to stop it, okay? And in fact, the Bitcoin staking protocol, I don't know what this is. There's a bit of a strange structure here. Do you think it makes some minor adjustment for me? Because this thing seems to be... It's pulling my glasses. You want it tighter? I don't know what's happening. I can't see it, so I don't know. It's pulling my glasses, I think. Feels like it's too tight. Muted for a second. All right, that's better. Thank you very much. Okay, let's continue. So this is hash time HTLC. Okay, so HTLC is basically in Bitcoin is almost like a one-trick pony. It's basically used in all protocols built on Bitcoin. So if you look at this situation, right, the secret revelation method is the core of the protocol, okay? In other words, how do you extract the secret when certain conditions are met or not met is sort of the heart of the protocol. And the interesting thing is that how this secret extraction works depends from protocol to protocol. So Lightning is different from Bitcoin staking. It's different from atomic swap, okay? So they're all very tailored to specific application, okay? And also in some applications like atomic swap, they actually depend on the action of counterparty. So there's some liveness problem in some of these protocols. So what we want to do in order to build a protocol for general application, okay, is basically to generalize the secret revelation idea for general NP relation, okay? So I want roughly the following. I want to say, okay, if you give me a witness and if this witness satisfies an NP relation, okay, then I can decrypt a secret and get the money, okay? So basically that's roughly what I want to achieve. Now, actually, people have thought about that, and the encryption method, okay, this problem is actually called witness encryption, okay? So if you could solve this problem called witness encryption, then if M is the witness, then if Bob can decrypt M, in other words, find the witness, then it can extract the secret if the witness is valid, otherwise invalid, okay? And so now you can use witness encryption to do a challenge-based version of secret, but now under general NP relation. So that would be super cool, okay? Unfortunately, if you talk to any cryptographer, they will tell you, forget it, don't worry about it. Witness encryption is a bad idea. Nobody has any good construction, years to a good construction. So this path is kind of a dead end, okay? Now, what is interesting is the development of a different method, okay? So BitVM3, okay, basically tells you that there's a different approach to this problem, okay? So now the flow is different. All right, so M is a witness, all right? Now Bob has to sign this witness, and Bob says, okay, this witness I assert is correct, okay? And then Larry is the challenger that will use the signed witness to decrypt the secret. And if you set it up in such a way that the secret can only be decrypted if M is invalid, then you can use this construction to construct a challenge-based scheme as follows. So Bob make a claim, okay? First, it needs to sign the witness, okay? Sign the witness, Sigma. You put Sigma on chain. And then Larry will go and try to decrypt the secret in such a way that if the signed witness is false, invalid, then the secret can reveal and stop the claim. Otherwise, after a certain timeout, the claim will succeed, okay? So the problem that Robin talked about earlier, called conditional disclosure of secret, is another cryptographic problem, but unlike witness encryption, this problem actually is solvable, okay? So that's basically what makes kind of this work, is the recent breakthrough in this BitVM3, and the BitVM3 construction is basically instantiating this problem of conditional disclosure of secret by choosing Lamport signature as the signature scheme, choosing Garbled circuit as the decryption method, and instead of sending the witness, you send the ZK proof of the witness, okay? And so this construction essentially says that Larry can now use this Garbled circuit to run effectively an off-chain SNOC verifier, okay? All right, so if we put it all together, we have a general construction, which is Bob will post a Lamport sign proof on Bitcoin. Larry will decrypt the secret to reveal S if this proof is incorrect, in which case Bob is blocked. Otherwise, after a certain timeout, Bob can redeem the Bitcoin. Okay? So this is the construction that will work. And very interestingly, there is quite a roundabout way of getting to this construction starting with BitVM, BitVM2, BitVMX, that was the talk earlier, and BitVM3 is basically using Garbled circuit to decrypt secret. In some sense, all this route is going back to the roots of Bitcoin protocol, which is secret revelation, which is HTLC. Okay, so people realize that maybe it's not that great a good idea to put the Bitcoin the ZK verifier on chain. Is a bit big. Secret revelation. Okay, and essentially this whole line of work solved this problem of secret revelation for general MP relation. Okay, so we did a bunch of experiments in the past few months to see what kind of performance gain you get going from BitVM2 to BitVM3, because we were debating which one to use. And so we did a very painfully expensive experiment. Okay, so a few months ago, we asked around, we said, hey, anyone actually put these challenge, what do you call these transactions? Assert transaction and disprove transaction. Anyone has actually put them on chain, on Bitcoin, the mainnet? And then no one did. I said, okay, that's not good. No one did. So we tried, okay? We tried. So the total is 5.4 megabytes, okay? 1.4 megabytes for the assert, 4 megabytes for the biggest disprove transaction, okay? So we ran through the unhappy path and we were able to put it on chain. Actually, there was a drama, okay? Because this assert, disprove is so big, it's 4 megabytes, okay? It was actually a little bit too big, all right? And I think some friends from Alpine Labs helped us to fix the problem of reducing the size by a few 10 kilobytes so that it just crossed the limit so that we can actually put it on chain. One observation is that these transactions are so big that they're non-standard, so-called non-standard transaction. So if you just try to propagate these transactions through the peer-to-peer network, it won't work. It will be stopped. And so we have to go to a mining pool like Mara has a service which allows us to submit non-standard transaction. As a result, we have to pay 3x than that day's transaction fee. So as a result, we pay $15,742. Okay? Now, it was a good experiment because it shows us how painful it is actually to get these transactions on chain. We have to go through a few hoops. And so it sort of gives us a stronger motivation to look more carefully into BitVM3. And so we redo the experiment with BitVM3, and we were able to put the assert transaction. The assert transaction is now about 100 kilobytes. Further optimization can be made, but this is the ballpark number. $93 only. Okay, $93 only. All right, I don't need to talk to our treasurer to get this money. Yes. Yeah, very standard. So the limit for standard is 400 kilobyte. That's the standard. That's a non-standard threshold. Okay. So we get 170x improvement. Robin mentioned something like 1,000-fold improvement. I think it's possible, but with our current implementation, we roughly get 170x improvement on chain costs. In terms of off-chain costs, okay. So off-chain costs, as Robin mentioned, the Citria friends did a very big effort in building the Boolean circuit for the SNOC verifier is 10.4 billion gates. 10.4 billion gates, okay? And we took that, and then we do optimization. We work hard in the whole summer, optimization. And finally, we get it down to a Garbled circuit of size 43 gigabyte, okay? 43 gigabyte. It has about 2.7 billion non-free gates out of 10.4 billion total number of gates. And it's basically this so-called privacy-free half-gate optimization. So it's one ciphertext per gate. Okay, it's 2.7 billion ciphertext. And the size is 43 gigabyte. After some optimization, some streaming, it takes about 15 minutes to do gobbling and evaluation, both are roughly 15 minutes on a single core. So if you want to do something like cut and choose, then you need to evaluate, let's say, about 180 gobble 180 of these guys. So on a 16-core machine, you can spend 15 minutes doing 16. So roughly speaking, we're talking about 150, 180 minutes, okay? About 2 or 3 hours. Because you can parallelize. All these are just different instances in a cut and choose. So roughly 3 hours on a 16-core machine for proving, and 15 minutes for evaluation, okay? All right, so these are the numbers. We're quite happy with these numbers because we plan to have an implementation where we reuse these circuits across different vaults. So we don't plan to use a brand new circuit for each vault. And so this basically proving time is basically a setup of the setup time that you can do once and then you can reuse many times, okay? So we're happy. We're cautiously optimistic about these numbers at this point. And yeah, so that's where we are. Okay, so we did in our white paper, we did a trust analysis. I may be running out of time now. What time, how much time do I have left? 6 minutes. 6 minutes left, okay. All right, so basically we did a trust analysis, trust assumption analysis on this vault. And we compare ourselves to the BitVM bridge that I mentioned, okay, and this is the vault. And we also compare to lending protocols that use this technology called discrete log contract, And we realize that it is not totally trustless, this discrete log contract, although it is native protocol built on Bitcoin. In terms of the Bob withdrawing collateral, the borrower, there's a trust assumption on Larry. And this is due to the fact that actually there's an atomic swap, which is folded as part of these discrete log contract lending protocols, which seems to be hard to get rid of. But using basically BitVM 3 instead of discrete log contract, you can make it trustless. Okay, all right. So what we plan to do is basically integrate these vault with existing lending protocols. And so the idea is that these vaults will be basically act as a form of collateral to be used in existing lending protocol. Okay, all right. So yeah, that's our hope, is that today we have this skinny bridges, trusted, centralized bridges connecting Bitcoin to the smart contract world. And we hope tomorrow, people will use these vaults to act as collateral and to participate in all these smart contracts. You can think of applications in addition to lending, like stablecoin issuance, perp DEX, etc. So in a white paper, we've gone through a bunch of these applications, and this is the world that we are hoping we will see in the future. And so I would like to acknowledge, very importantly, we collaborated very closely with all kinds of people, cryptographers, BitVM Alliance, as I mentioned, we benefit a lot from Citrus implementation of the Snox Growth 16 verifier. And so thank you very much to them. All right. And yeah, so this is the white paper. If you're interested, please take a look. Actually, our team is here. Okay, our team is actually just across the street. We're hacking away, and we're trying to do a 2-week sprint to build this vault, a proof of concept. So they're now working. I'm talking. They're working. All right. And so these are the guys. They're working right there. So hey, we're looking for great people to join us in this effort. This project, if you love technology and cryptography, it's a beautiful project, okay? It has Garbled circuit, so MPC. It has zero-knowledge proof, ZK proof. It has smart contract on Ethereum because you have to integrate with smart contract. It has pretty complex Bitcoin scripting. And so it has kind of all kinds of things. So yeah, we're looking to hire new people. So please let me know if you're interested. Thank you very much.
Thank you, David. we have time for 1 or 2 questions.
Thank you. This is a cool construction. First of all, the QR code doesn't work. So I'll come find you later to get a copy of
QR
it.
code doesn't work.
It says it's deactivated. You need to buy a plan of some kind. But I mean, you spent $15,000 on transactions, so.
15, not 50.
15, okay.
15.
Yeah, so okay.
50, I'll get in big trouble.
My actual question is, you mentioned the ability to reuse the circuit. Could you maybe say a little bit more about like the nature of that reuse? I assume you mean like the reuse of like a cut and choose set of specific garbling tables? Or do you mean the circuit topology?
The reuse construction is orthogonal to cut and choose. Right? Cut and choose is a proving mechanism.
Oh, right, yeah.
You can use many different ways of proving it.
Right. I just mean like, but I mean, it's effectively like one single instance of garbling. When you say reuse, you do mean like reuse a garbling table and not just reuse the circuit topology?
Yeah, of course. We're reusing the same garble circuit, right? What is the garble circuit? It's a bunch of encrypted data. And once you use it once, then it's over, right? So the reusing is achieved by reorganizing the transaction graph, okay, in such a way that if you basically have one garble circuit, every challenger prover pair.
Okay, that was my question.
So that's the construction.
Okay, thank you.
And I would expand on that. So in this specific case of lending, that means there's between every borrower and every lender, there is a specific garbling table, right? So that also means that if one of the parties, or actually in this case, it's just one of the parties that can misbehave, right? You would then slash all the instances that they have. So if there are 10 loans outstanding, and if one party like tries to attest to a wrong computation, you would slash him in all 10 instances, right?
Yeah, so that's a very, very, very important question, okay? So reusing a garble circuit has an implication, okay, which you can either think of as a feature or a bug, okay? And the property is that once you are caught committing a crime in one peg out, then you are not allowed to peg out anymore from any vault, okay? So you can think of that as a feature, or you can think of a bug, okay? But in any case, I don't think it's avoidable if you want to reuse the circuit, okay? Is that your question? I think that's your question, right?
Yeah, just one final question before we need to wrap up here.
Yeah, this is really interesting direction. It's cool to see you guys work on this. We walked through the lending example, I guess, in the slides, and you mentioned Trustless. I think you compared it with the discrete log contract-based approaches too. Where does like Oracle, something like an Oracle trust assumption fit into all of this? Because
yes,
we looked
yeah, good question. Sorry, I forgot to mention that. So in any lending protocol, okay, there is an oracle, the price oracle, okay? So the comparison here, oh, what happened to that table? Okay, never mind.
Oh, and that's our timer to suggest that maybe we need to wrap things up here.
The comparison here is assuming a good oracle. All 3 columns have the same assumption.
Thank you. Let's hear from David. Okay, now we have a break for...
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Plus Scaling Edition, September 3rd to 5th, 2025.
Welcome back to the main stage at Bitcoin Plus Plus Scaling Edition. My name is Walton. I've been emceeing today, but I'm delighted to be able to moderate another panel here at Bitcoin Plus Plus. Thank you. Thank you, super. The ARC, of course, was boarded 2 by 2, and that's exactly how I'm going to do my speakers. So, to begin, the two gentlemen from the two ARC teams, Stephen Roos from Second, and Alex B. from ARC Labs. And the next two of my favorite developers who I think are deeply passionate about self-custody and enabling more freedoms for people to transact on Bitcoin, how they want to. The one, the only super testnet. And one of the pioneers of mini-script, Salvatore Ingala. Thank you. Super. Can you move up one, please? Thank you. Okay, so as I'm sure each of you, the people on my panel know, in the Lightning white paper, they said for Lightning to scale to everyone in the world, we would need, is it 133 megabyte blocks? And we don't have that size block. And so we're all here today because the layer of Lightning and the main chain have their limitations with regards to how many people are able to use them to transact in Bitcoin.
Their math was wrong. They were assuming one transaction creates each channel, and if you do batching, you can fit in more. But you still need ARC, even if you optimize in that way.
So what I want to know from all of you is how can we how do we best batch transactions, and maybe for some people at home, how does that outprice other kinds of transactions?
ARC is a great way to do it because you can pack a whole bunch of channels into one output. So that's one thing you can do with ARC. Are either of the ARC teams doing that? You making ARC into like a channel factory type thing?
Soon.
Okay, cool.
Yeah, I mean, going beyond or before making Arcade into a channel factory, like we like at Arcade and with Arc Labs to refer to ARC as a transaction batching system. I think fundamentally it's what it is. And I think it's a useful construct because it allows you to think even beyond kind of like the sort of focus on payment system. And therefore, what do you actually do is you can, yes, batch channel operations. And so to Super's point, like the math of opening channels in and out of Lightning, and the idea that everyone would need a single channel that would be open and enforced on chain was indeed, I mean, the math was right, but it did not anticipate the fact that perhaps we would be living in a world where users did not need to have a Lightning channel of their own to interact with Lightning, but would be able to simply swap in and out of Lightning using UTXOs or, in the case of ARC, VTXOs. So this is something a lot more that resembles what, kind of like something like Moon pioneered, which was, this great UX of not having to be concerned about liquidity or channels and just swap in and out. Obviously, that did not scale, although it provided a greater user experience. We saw during the Ordinals event that, people literally had to stop using Moon because it was broken. And that's kind of like, that's by design because doing swaps on chain gets expensive. But the ability to do swaps in using VTXOs, which, when you're doing swap using VTXOs, are you actually, is this a payment or are you actually, using ARC in a kind of like programmable way with using VTXOs? We think it's more of the latter, which is, why the conversation, at least on our end, has shifted from ARC as payment to ARC as kind of general programmability. But maybe you guys can add to that.
Yeah, I think just general, although one of Barak's original intentions for ARC was you could use it as a way to pack more channels into a thing, you don't have to use it that way. It also works for payments internally on the ARC and through swaps. You can also interoperate with the rest of the Lightning Network without giving everyone a channel. So there's alternative ways to use it, and it's not necessarily like now we can do what the Lightning Network's paper thought we couldn't do. We might just not need to do that anymore.
There are some benefits that come from doing channels, though. Like in our implementation, Bark, we're also doing the way where you swap into Lightning and out of Lightning using HCLCs inside the ARC, which is very convenient, right? It's very easy to implement, and it's very easy for the user because you just make a single payment inside the ARC, and then you get your payment forwarded on the Lightning Network. But I mean, if you're, for example, receiving lots of payments, right? In this model, for every payment that you receive, you would have this like VTXO blob, which is a bunch of transactions, and that has some kind of cost in case you would have to exit it. And if you receive hundreds of payments and you need to manage these hundreds of like different VTXO blobs, it can be spread out of like many different on-chain transactions. Then a channel actually becomes very useful again, where you can then like have one VTXO where you can receive hundreds of payments off. And every month, you basically reset your channel, you refresh it into a new VTXO, and then you can make hundreds or more payments again into the same one VTXO. It comes with a lot of the other challenges that Lightning comes with, right? So the server needs to decide how much liquidity to allocate to you in the channel. That's why like the naive implementation of swapping is definitely easier, and we implemented that first. But we definitely plan to extend and have virtual channels in our ARC so that you can get like the higher like bandwidth or throughput that Lightning gives you.
I think taking a small step back, a broader view on the scaling question. So we're talking about how to scale payments, which was how do we fit all these payments in one blockchain which has limited space. And if we focus on things that we can do in a trustless way, so without using custodians, without like making sure that you know that you have your money, there are two things you can try to do basically. One is try to make the transactions smaller so that if transactions are smaller, then you can fit more in the same space. And the other is transaction cut through, which is if I send money, if Alice sends money to Bob, Bob sends money to Carol, then maybe the first two transactions can be replaced with a single transaction that is money of Alice going directly to Carol, right? And so making transactions smaller is something that, of course, we can engineer Bitcoin to improve which opcodes we have so we can do certain things, but it's probably mostly something that's explored in sidechains and these layer 2s that try to do alternative blockchains that use a different representation for transactions. Maybe they don't use a full 32-byte public key to identify the user. They use something smaller, so this allows them to compress more. While things like Lightning or Arc as well, what they enable is to keep a lot of transactions actually off the chain so that they enable to actually do transaction cut through because it's only a settlement time that you check the initial state and the later state. So yeah, making transactions smaller and transaction cut through, those are probably the only two trustless scaling techniques that we know, I think.
Well, the other thing you can do is make bigger blocks, right? Which I think, when you're taking transactions off-chain, there's no bigger block than the whole wide world outside of the blockchain. Like, if we put all of our transactions in the outside of the blockchain space, then we've got massive, massive sizes. Like, you can fit anything in there. It's the whole internet is your block size.
Is it trustless though?
But it's pretty good. It's pretty good. The Lightning Network's pretty close, but nothing's trustless.
Yeah, I mean, if we have off-chain block space and we have like hundreds of gigabytes of VTXOs and suddenly the server disappears, like those hundreds of gigabytes of VTXOs need to get on the chain then, right? And it's like how many of these people actually can get on the chain? So there's still like the limit. There's actually a limit on number of VTXOs that can exist safely, and that's based on how much of them actually could get on the chain within the lifetime of the VTXO. But yeah, I think that limit is definitely a lot better than people actually having to make 1 or 2 transactions on chain every year, like they assume.
Hold your mic closer. Hold your mic closer to your mouth.
Oh, sorry, yeah. Like in the Lightning paper, like you were saying, 130 megabyte block. They were assuming every user would like have to make 1 or 2 channel interactions on chain every year. And I think with Arc, you don't have to make any of them as long as your server is cooperating and like running. So I think it's a lot better.
Yeah, and it's something that's interesting with Lightning and Arc also that differs from some of the other models that I think were discussed throughout the day is this notion of scaling, which is that in both cases you're not actually creating another blockchain where you have kind of like the same scaling limitations and kind of like bottleneck that any other blockchain has, in the sense that, I mean, to what Steven said is correct in a way. Like there's limits to, how much you can keep this sort of non-batched, non-pruned set of VTXOs off chain, but at the same time, at least you don't run too much into kind of like the data availability challenges that systems like rollups introduce, where there are not theoretical but very practical limits to how you can scale. At least, EVM-style roll-up models where eventually, if you want to do that in a trust-minimized way, you need to put that data on-chain. Certainly that data is compressed, but there's very practical limits to how much that data can be compressed and can make it onto, and how much of it the Bitcoin blockchain can support. So having a system that doesn't really reintroduce a global state, like what Arc or Lightning does, has very practical and kind of like, we think considerable upside that really remains unexplored in terms of theoretical throughput, if the goal of this exercise is really to be able to support a global financial system that is backed by Bitcoin.
Is self-custody binary? is if you hold Bitcoin.
If not, I'm not judging.
Please join the hackathon where Super Testnet will be judging. It begins tomorrow. Please attend the briefing. Is self-custody binary?
Yeah, no, I think it's very much a spectrum. Yeah, we've seen. I mean, like I was saying in my talk earlier, it's definitely because of the restrictions of what Bitcoin actually offers in like terms of expressibility. Right, if we would have more expressibility, we can actually make it like less of a spectrum. But because we don't have that, like things like covenants, things like introspection, we kind of need to make trade-offs because with what we have, we can do very little in a fully trusted way. So then we kind of like bridge the gap. Like there's this like fully custodial model, you have on-chain payments, right? And between that, you have all kinds of different trust models that exist. You have the liquid model, you have the Spark like state chain model, you have then things like Arc, and within Arc even you can make different types of trade-offs to make trade-offs between UX and like security. So I think it's very much a spectrum, and we're just feeling what users are comfortable with, what UX people accept, and stuff like that.
I think it's interesting you use the word trustless as well as saying that it's a spectrum. John Light, who I believe is still with Alpen Labs, last year was explaining to me that the concept of to what degree you trust the system is a spectrum, and so Lightning is perhaps the most trust minimized, although I know Supertestnet has issues with that term, of the layer twos, for perhaps want of a better word there. To what degree do we agree with this statement, and yeah, where do the other ways to interact with the chain sit on that spectrum?
I think Arc is at least equal to Lightning in that respect. It's well, not at least. It's very, very close to where Lightning is on that respect. Like, but in both Arc and in Lightning, you have a certain number of transactions that you have to broadcast in order to exit. And I think the worst case in the worst case in Lightning is, I think, worse than the worst case in Arc. Because the worst case in Lightning is where you have all of your HTLC slots filled up and you have to exit in that state, and it's like hundreds of transactions to exit from Lightning. Whereas that doesn't really happen in Arc. I don't think there's any models where it gets to hundreds of transactions to exit Arc. So it's like, I think the worst case in Arc is better than the worst case in Lightning, but the best case in Arc is also worse than the best case in Lightning. Is that fair?
I mean, I'm going to go against my book because I'm obviously implementing Arc, but I think the worst case in Arc is definitely worse. I mean, the worst case you're describing in Lightning is if you have 100 payments ongoing at this moment, which no one has, right? Usually people have no payments ongoing when something goes bad, or maybe one.
Well, but that's the attack. The attack model is that you do that. You get someone to have a bunch of HTLCs in flight and then close the channel and then force close their channel.
But if you're an end user, you just don't accept those HTLCs, right? You're not a routing node. You don't just accept random HTLCs, right? You can have a limit of one. I mean, the worst case, like every single VTXO in Arc needs a sequence of transactions to exit, so anywhere between like maybe 3 to like 7 or 10. And every one of these has a fee, and like the minimum number that you can securely hold and actually have a guarantee that you can get it back on chain depends on how much transaction fees you're going to pay for all these transactions. And in the normal case in Lightning, that would just be like 2 or 3, right? Most people that are leave nodes in the network, like end nodes, they would just be having their own HLCs for their own payments, which is usually one at a time, right?
I think like another concept that's coming up a little more, like if you follow, for example, the work of Janus at Bitcoin Layers, is this idea of finality, which I think is just as important as self-custody, because finality kind of expresses the reliability of execution of the system, and it applies, and it's kind of like a necessary concept because it applies to a lot of these new systems like rollups, like Arc and state chains, where you do have kind of like transitionary period where you depend on the operator of these systems for the execution, meaning that unless you include, for example, in the case of Arc, you can chain transactions off-chain and have a bit of a state chain trust model, right? Where you effectively rely on the operator and the previous owners within that chain of transaction not to collude and effectively reorg. But what happens when the when you know the operator, a malicious operator, would reorg is you have two users with a set of conflicting transactions that effectively have unilateral X, the ability to claim the same UTXO on chain. And so theoretically, both users have self-custody of that UTXO, but it's a matter of who can actually enforce it. And for various reasons, it's likely that the attacker is most likely to be able to enforce it before the victim. But finality is important because you have within Arc, when you're considering this idea of joining rounds, or in our case with Arcade, kind of like including the payments that you've received into a batch. This is how you actually achieve Bitcoin finality, meaning that you've received a set of off-chain payments, and then you have them included into a Bitcoin block via an Arcade batch, and therefore you remove the dependence on the operator. And this is something, for example, that a system like Spark is not able to offer. So a system like Spark, that relies on state chains, the only way for you to achieve finality, although they will certainly make the argument that users of their system have self-custody because they have a unilateral claim on chain, the only way that you're actually able to achieve Bitcoin finality for the set of transactions you've been involved in is to effectively withdraw your money on chain. And this kind of in a way defeats the purpose a little bit of scaling systems, because we're building those systems to be able to avoid having to pull your money on chain and bear the cost of these transactions. This is also something that applies to roll-up style models. More so in the context of full zero knowledge validity rollups, where you have an operator that sequences transactions off chain, but in between state commitments on chain, there is an opportunity for the sequencer to actually also reorg the execution. And the execution is primarily important from the perspective of perhaps other applications of these systems than strictly payments. So, from the perspective of people that are doing, for example, swaps and trades within these systems, if you have an order book, decentralized exchange or trust minimized exchange, if you will, well, the fact that potentially your trades can be reorged the reliability of execution is perhaps as important as the self-custodial aspect, because you're perhaps incurring massive economic loss if you're making the price of whatever asset you're trading changed dramatically, and you're trying to maybe get out of that asset, and that trades get reorg. Well, in the case of rollup, they have a bridge system, and the cheater maybe cannot get their money out of the system, but what you really care about as a user is that you cannot go back in time to reinforce that trade again, and so you effectively potentially lost a large amount of money because you're not able to enforce that trade. So again, I'm bringing a different aspect to this self-custody and finality conversation, because in this direction that we're going, I think it's just as important to build systems that perhaps are not trustless or trust minimize as much as Lightning is from the perspective of this ordering of transaction. But what you want to do is build incentives and build systems that are robust enough so that the execution of these transactions is also reliable until the time where the users actually achieve full self-custody.
I think there is a bit of a communication problem often when talking about these things, because self-custody, you can say it's a spectrum, but I think it's even more complex than a spectrum, because you cannot put a number on how much self-custodial something is. You cannot say oh, Coinbase is 0, Lightning is 1, and you say oh, where is ARC? Is it 0.9 or something? So there are many different trade-offs, many different trust assumptions that different systems make. So you cannot even necessarily compare one with the other to say, oh, this one is more trusted than the other, because the trust assumptions might be quite complex. Like who is able to rug the user, when they are able to rug the user, are they able to rug the user at all times or only at specific times, only at the time of a trade or during the whole time? So I tend to be very religious on how to use the term trustless. For me, anything that requires more trust assumptions than Lightning, I don't like to call it trustless, while I'm more lenient with the term like trust minimized. But trust minimized by itself doesn't mean anything, because trust minimized can be a 3 of 5 assumption, can be 1 of n, can be many different things. So
it always means as trustless as I could think of how to make it.
Yeah.
And it's
And it's a bit like, of course, it's a marketing problem in a way because marketers, of course, like to say, oh, we are trustless or we are trust minimizer and everything, while researchers are more into like, okay, what are the differences? Like, what are exactly trust assumptions? And it's very difficult to convey these things to the final user, to the potential customers, without using a single word, but there is no single word that works. So it's a complex problem.
Yeah, as my friend SuperTestNet told me earlier, the minimum amount of trust is 0, and so if something is trust minimized, it doesn't make sense because they could make it smaller. If we look at on-chain fees today,
what on-chain fees today?
Thank you, Super. Exactly. Is this not proof that Lightning is providing sufficient scalability for everyone that wants to use Bitcoin if the on-chain fees are still in single sats per VByte?
Sure. Yeah. For the few hundred people who are using Bitcoin today on a daily basis, right? So
half of which are here today. Thank you very much.
And we're not making any payments today. So no, I mean, people are saying things like, oh, aren't like on-chain fees too low and all that stuff. But I mean, I think we're like incredibly early. Even most Bitcoiners, even people who like are deep into this tech and use it a lot relatively, are not using it only a fraction of what they use like normal payment rails for, right? So we have like probably another like 9 billion people or 10 billion people to onboard on this system if we want this to be the global money. So I think we can be very glad that the fees are low right now because no one's actually doing anything. And it gives us hope or space to like onboard people and actually have them have an experience that is not horrible, because I think as soon as you onboard like a few million people, it's gonna not be 0, it's gonna be like something, and then the rest of the world still has to come. So yeah, I mean,
I think what the low fees more shows, or one of the things it shows, is that a lot of people are using custodians. If you look at Nostr zaps, if all the Nostr zaps that you can view on the Nostr network were put on chain, they would fill up we would have full blocks. But they're not doing that, and if you look at what wallets those zaps are coming from and going to, they're all custodians. Or they're mostly custodians, like 95% or something are custodians. So it's not exactly that people are using Lightning. They're kind of using Lightning, like they deposit it into the custodian using Lightning, but then they're just like updating balances within that custodian and sometimes a couple of other ones.
Yeah, I mean that's completely correct. I think there was this notion, I think, in the early days of Lightning where we would kind of like fill up the blocks by having channel rebalancing operations. The problem with this notion is that it kind of like assumed almost kind of like this notion of like permanent like imbalance between in channels, right? So you have to rebalance your channel because somehow like the channel got emptied on one level or another, on one side or another. But I think what we're finding out right now is because the self-custodial UX around Lightning has been so painful, people therefore have been using custodial Lightning wallets, and custodial Lightning wallets is a great fit for Lightning because it involves like Super said, a set of wallet providers that have Lightning channels between one another. And fortunately, the way that they use Lightning is how Lightning really should be used, which is they have bidirectional channel with balanced flows. And if you have balanced flows, ideally you can avoid having to close or open channels or as much as possible. Certainly there's some cleanup to do and operational stuff, but beyond that, I think I think we had an early period of Bitcoin or Lightning where we're actually kind of like in a way really misusing the block space because we were trying to fit this Lightning model into applications where you would have only unidirectional flows. Where basically you would this notion of merchants or streaming where everyone would be sending money in one direction would create sinks, basically liquidity sinks in the network, and these nodes would have to always kind of like do on-chain operations to rebalance, and therefore requiring on-chain operation. I think what happened in these kind of applications and these kind of behavior on the network have effectively trended down because it's economically inefficient. People have had the misfortune of having, channels open with people that were forced closing them or whatever. So Lightning as a whole has professionalized, has become a lot more, institutionalized almost, and it's being used the way it should be. It should really be used. Now the missing, element here has been, well, how can we leverage this, optimized architecture for Lightning without having to depend on custodial? And again, I think both teams working on Arc feel like, this has been the missing key there to provide this custodial type experience without having to introduce, this imbalance of liquidity that is effectively, an economic opportunity cost. So when people talk about Lightning and the UX struggle around making self-custodial payment, at scale, the reason why at least personally, I don't think this model of, self-custodial channel-based Lightning wallet is unsustainable is not because of the UX. It's because economically, it's almost impossible for that to scale, because you think of a model where Phoenix have 10 million channel open with every single user, and they have to commit funds to that channel, and they don't know if that liquidity is actually going to get churned, and therefore they have to charge higher fees to commit that liquidity, and therefore making the Lightning experience more expensive than it should be. And I think Steven's team has done great work putting up a blog. I think Matthew put out a blog post demonstrating that actually, the ARC liquidity model is probably optimal in a lot of cases because you don't really have this sort of stale liquidity floating around the network.
Yeah, that's actually like unintuitive, because in the very beginning of ARC, one of the main questions that came up a lot is like, oh, but liquidity, like you need so much liquidity, it's gonna not work. But if you do the math, like you actually need way less liquidity than an LSP would need, because an LSP needs to dedicate a specific
directional
piece of liquidity, to each user, and it needs to kind of know how much is this user gonna receive in the next year, 2 years. And that's kind of impossible. Like a user can receive a lot of money because he's doing organizing a summer festival one day, and it's like, oh, he needs a new channel. He was receiving a shitload. We're gonna put loads of money in liquidity, and then the whole year he's not doing anything, right? And that's an impossible task. While in ARC, the liquidity is only needed on a payment per payment basis. So if users don't make payments, they don't really have a liquidity requirement for the server. If they make a lot of payments, they have a higher liquidity requirement. But that's natural, right? If users use the system, they have a liquidity requirement. If they don't, they kind of don't, or at least minimal. So yeah, I think ARCs are way more efficient in terms of allocating liquidity to your users than I think the LSP model is. That's not to say the actual Lightning model, right? Custodial Lightning is kind of 100% efficient because the bank or the custodial just owns all the money and is just wherever it wants it to be. But yeah, for non-custodial models, I think ARC is definitely.
But I think that the paper you're referencing, which is a great read, by the way, I learned a lot from it. That paper talks about how the numbers change if you're making a lot of payments, and it only gets better than the Phoenix model if users don't make a lot of payments. If users just receive money and then don't spend it, right? Is that
yes,
accurate?
Yes, that is correct. Yeah, but. I mean, for the foreseeable future and some years, I don't think people are going to make too many payments. And once we're there, we can do virtual channels. And virtual channels gives you the benefit of not needing liquidity for lots of payments, but also not needing to predict for the next year how much this user is going to do. The server kind of in a virtual channel model gets a free chance to rethink how much liquidity to allocate for each user every 30 days, right? Because every 30 days, you need to refresh your channel into a new VTXO. So then you can kind of get best of both worlds. Users that don't make any payments or not a lot of payments, they basically get the really low liquidity. People that do a lot, they can get a virtual channel, and if they suddenly stop making a lot of payments, then just the channel can just be refreshed into something that's not requiring a lot of liquidity. So I think the virtual channel model gives you best of both worlds in this case.
Go ahead.
Well, I mean, I think even before we get there, the other aspect that's perhaps not covered as much in the paper because it's hard to anticipate how users are going to use the system is with ARC, you also have this kind of knob of off-chain execution that you can control as a user and actually selectively kind of voluntarily kind of opt in to a model that perhaps is a little less trust minimized, right? Where you actually make, because like when Steven said like you need liquidity on a payment per payment basis, that's also not necessarily true, because you can just chain payments, a lot of these payments off chain, and eventually you can decide to settle them into the rounds, into the batches, where this is where you actually incur liquidity costs. So like you have a whole range of like design that's going to probably be used in different ways by different applications, by different wallet, or eventually the end users is going to decide, well, if I'm okay, if users are really okay with the state chain model, there's an opportunity for the users to not have much economic cost at all in terms of liquidity for the operator. But then for higher value transfers, if you're transferring $100 million, then certainly you want to diminish your risk exposure to the ARC operator as much as possible. So you're going to immediately kind of like settle that payment into a round, and therefore get. Coming back to that Bitcoin finality term that I was saying, is like you want to finalize that transaction as soon as possible, because it's a large transaction. So that's another design space that ARC offers that is not really like available to Lightning. I mean, I think there's a caveat there that you can hack some stuff, but it involves probably a bit more complexity.
Yeah, it does. You mentioned if you're doing $100 million, I also don't see a soon future where that kind of liquidity would be deployed to ARC. Anyone who would deploy that kind of money would probably just put it in a single multi-sig wallet.
If you plan to do that, definitely give us a phone call before you do that.
Okay, I will.
Why is ARC better than eCash, or is it?
ARC is eCash. So all of Bitcoin is eCash, right? What's the white paper say? Bitcoin, electronic cash system, and ARC is just a way of handling Bitcoin. So, what I think you mean is why is ARC better than the Xiaomi and eCash mints?
Than Cashew, than Fedimint.
Yeah, those aren't the only things that are eCash.
Sure, super. Thank you for clarifying.
Well, you go ahead.
I mean, because it's non-custodial, right? I mean, we were actually having a conversation here earlier. Like, there's several reasons. I mean, I often question to myself and to people around me, like, where does the demand for self-custodial things come from? Is it because doing custodial things is just illegal, and it comes with like a lot of regulations, rules, and all that kind of like stupid regulatory bullshit that people don't want to do? Or do people actually want to be self-custodial? And we don't know, because we live in a world where to do a custodial solution, you need to go through all these hoops and all this like regulation and government stuff, and that's why no one's doing it, because it's kind of impossible. Like a bank cannot offer an eCash solution, like fully private, because it goes against all government laws. So maybe if that was not the case, maybe we would all be happy with just having a few eCash mints and just have a few banks that are quite trusted and operate in a judicial system where they can get recourse if they try to rug them. But maybe not. I mean, I personally believe that there is real demand for self-custody, even in a world where eCash mints would be able to operate on like large scales, because I think the permissionlessness and just the like peace of mind of not having to deal with like third parties just is something that people will want. At least some people, right? I think enough people that we're building these systems also for people that would not use the custodial solutions, even if they would exist. But I mean, eCash on the UX front is just the best, because it's like instant, it's fully private, you can do anything you want.
You can do it offline, right? We're like,
yeah, but it is custodial, right? So then you have to make this like choice: do I want to not be custodial, or do I want to have like the best UX possible? And I mean, it's again some kind of like spectrum between UX and self-custodial, and I think there is demand for the non-custodial solutions where people can have peace of mind that they can like be totally independent of like third parties in their jurisdiction, because maybe they don't live in a good jurisdiction or something like that, or maybe they want to be nomadic and be able to move from one jurisdiction to the next and all that stuff. So I think there is demand there will always be demand for self-custodial Bitcoin payments. I mean, that's why we're all here, because we think self-custodial payments are like good for financial independence and freedom. But yeah, it's another which is best. It's more like what do you choose?
Yeah, there are definitely like solutions to different problems, but like, I mean, I think I would challenge and this is speaking from someone that went into a huge like eCash rabbit hole last year, which usually is my thing. You know, I just change my mind very quickly about a lot of different things. I still think, you know, eCash is an interesting project, but I think I would even challenge that the UX for eCash is superior to everything, because like you're still having to manage like a private key, and like there's still scenarios where like, you know, it's completely custodial, but you have to manage a private key. You lose your money, you're in a world of pain, really. And you know, with Arc, like, which has, you know, so certainly it doesn't have the privacy, at least not baked in privacy aspects that eCash offers. But from the perspective of like UX, if you are okay with the trust assumption of eCash, you can pull off pretty decent, even arguably superior UX, I think, with just like vanilla ARC payments that you can. And you even have the benefit of having recourse in terms of like, you know, losing your ARC keys. Because there are scenarios, you know, where, you know, there's this concept of ARC VTXOs having expiry, right? And obviously the early conversations around this was like, and I think, perhaps Super was adamant that if the ARC, if the VTXO expire, the operator is going to run away with it, or at least you shouldn't trust him.
Only in my implementation.
Yeah, well, yeah, exactly. But you know, there is a scenario which is actually, you know, potential feature, right? Because it's like, well, say your mom lost her private key and she has ARC VTXOs. Well, there's a scenario where you can actually she can actually retrieve that money by collaborating with the operator. That's great UX. But the other thing that I wanted to say is like, why is like ARC different than eCash? And what I really, really like about ARC, and why ARC is, I think, different than every other system, and is in a way similar to Lightning, if you will, is like it does not really introduce any new technology to make like the system work. Right? You're only talking about things that are already available in Bitcoin. Like you're not requiring additional cryptography, which eCash requires. You're not requiring additional cryptography, which again, like BitVM requires. You're simply dealing in MuSig2, Taproot, and pre-signed Bitcoin transaction. So it's fundamentally a very, very simple system. And it has also all the great properties that, you know, we've discussed. But, you know, I think this is something worth pointing out because it really is an advantage, because it also allows us to rely on kind of like the accumulated knowledge of developers having, you know, when you're talking about MuSig2, you're talking about something that's, you know, been audited by, you know, smarter people like Salvatore, or maybe even smarter people than him. So you can, you know, you kind of have good confidence that this is a system that's production ready and can actually be deployed at scale without too much concern. I'm not saying that the cryptography in eCash is terribly complicated, but it's an additional set of assumption that you're making.
Thanks for the shout out. I cannot audit cryptography, but I implemented music too. But yeah, one thing I want to say, so to compare the two systems, so today most people use custodial systems with no privacy. Arc it's fully self-custodial, but in the current form today probably doesn't have great privacy. eCash is the opposite, so is fully custodial but has great privacy. And we are not done working until people are doing self-custody with good privacy, right? That's Arc in the current form is not what it will be in 5 years from now, probably. There will be ways of improving it. If we get covenants in Bitcoin, there could be many ways of potentially improving Arc. I'm really excited about the general framework Arc is working with, because I think it solves a lot of the engineering difficulties that Lightning has, but it's not a finished project, and is not like Arc today is not the only way you can think about this kind of layer 2s.
When you said that eCash or Xiaomi and eCash mints have the best UX or something to that effect, He gave all the reasons why I disagree with that. And I agree with everything he said. But there is one aspect in which I really agree with it, that eCash has better UX than even Arc does. And it's something that you guys can fix. And so I'm going to hereby request that you do this thing. When I make an eCash payment, almost every time, I create an eCash token that has a certain value, and I give that to whoever it is that I'm sending money to. Whereas with Bitcoin, typically, I get something from them first. Like even with Lightning, I get an invoice from them first, and then I pay that from my wallet. I really like the token model where I create something of value and then give it to them. And you can do that with Arc. So I recommend making that a standard way to pay people. Is you don't need to get something from them, not even a public key.
We do that.
You currently do that?
You need a public key, yes.
Yeah, you don't, but you don't actually need it in Arc. You can do it without a public key, and so I encourage you to make it so that you don't need one.
I mean, I think if your assumption is to create, if you're okay with trusting the operator, then we currently do that in Arcade, which is, we call it an Arc note, which is effectively Arc credit, which allows you to, but again, you're trusting the operator entirely to allow you to redeem that note.
That's not but the way I'm thinking of doing it is you create a public key or a private key and a public key, send money to that within the Arc, and then give the private key to the person you want to pay, and then they can now they have it. That's the way I would do it if I was you guys. I would make that the standard way to pay.
It's possible to do. It's not hard. I'm not seeing the value too much. I mean, usually when you're going to pay someone, you know something about that person, like their address or something, or you have a way to communicate with them. I mean, in almost all scenarios, that's the case.
I'll talk to you after about why I think this other model is better.
I mean, it's interesting from the perspective of UX, and I think you're right from the perspective of replicating something that people are familiar with, like tap to pay, right? So you can potentially do, potentially recreate that UX by doing something like that, which would not require scanning a.
I hate scanning QR codes.
Yeah.
But tap to pay in like fiat systems is also a very interactive protocol where you do like multiple things. Like it just happens real fast in like micro scales, and you could do the same with Arc. Like you would have some kind of card that's Arc enabled. It would get some public key from the thing. It would sign something, put it back, and then done. Like I think tap to pay is not necessarily a push-based system either.
So it seems that you all agree that there are trade-offs to different ways of paying in Bitcoin, whether you're using Bitcoin, Lightning, eCash, Arc, or other forms. What I'm hearing is that people like Michael from Boltz are going to be making a lot of money. These swap providers are going to be powering the future. But we live in a world right now where covenants aren't enabled on Bitcoin. To what degree do my panel? To what degree are my panel for covenants? And yeah, which ones do you think may or should get activated soon that may help other scaling solutions like Arc, etc.?
The reason I take exception to that is that you can emulate covenants in Bitcoin today, and what you can emulate, you have. The way you emulate it is using multisig. So I say we do have covenants. You just have to be part of the quorum, and it has to be n of n. But there are ways to do covenants that make it easier, and the ones that I think that I want to throw my hand up in support for on this panel is the CTV plus CSFS thing. Let's do that one. Yeah. So.
Sorry, personally, I support all opcodes. I have been pretty vocal about the fact that whether it be opcat, whether it be optxash, whether it be CTV, checksig from stack, I am one of the people that is, I think, least afraid in this industry about the prospect of like things like MEV, which has kind of like been a bit of a spooky kind of it's something that's get brandished a lot from the prospect of activating more advanced covenant. Of course, there's a conversation around implementation, complexity of all of that other stuff. But I'm generally of the opinion that any form of introspection is relatively harmless for the system, and I welcome everyone to kind of like introduce that into Bitcoin consensus. Certainly, I would not advocate against it in any way, shape, or form. I don't want to speak for my team, but I think most of them are generally directionally in agreement with this. But again, the challenge is to create a compelling story for people as to why any of this should happen. And I think this is where, you know, our focus, and I think this is why I like, you know, this is like ARC, I think has been usually beneficial for anyone who's working on it, is like it actually allows us to build a system that does not require any changes to Bitcoin and can potentially be used, you know, once deployed and once put in production as a very strong argument for why, you know, new features could, you know, reinforce and benefit further the deployment of system like ARC. And so I'm, you know, I've always been a little bit uneasy, kind of, you know, banging the table for something that would certainly benefit what we're doing, but what we're doing has no product market fit at all in the current form. And so, you know, I think maybe even just a year from now, we'll be in a much, much better position, whether because BitVM also base solution have been deployed, or whether it's ARC and Arcade and Second, you know, we'll have some kind of like market feedback from what people actually want to use. And, you know, the argument, so it's like, again, we're not going to, I think generally I support all of that stuff, but I'm not going to die on that hill today. And we're fully committed to build something that we think is going to be awesome without any change to Bitcoin at the moment.
So I'm a bit biased because I gave a talk on changing Bitcoin in which opcode I like earlier this day. But yeah, generally speaking, yeah, I'm also quite open to changing Bitcoin in ways that especially can improve on scalability, privacy, and self-custody. Those are the only three things that I care about. And yes, I think there are definitely some changes, some smaller or some bigger changes that we could do that could improve a lot in these things. And yeah, I'm biased also because I'm working on one opcode proposal called check, contra, verify. Best covenant, check it out. But yes, I think it's also true what has been said here, that there are ways of kind of simulating the covenants with other approaches that are not, of course, fully trustless. There are some degrees of trust minimized. And I think we'll see more of that in the next few years when people want to use covenants and they don't have covenants, they will find ways of simulating them. And I think that will be great to actually show actual usage and demand in practice.
Yeah, I think ARC is actually like a very nice project in like this pursuit. I mean, I obviously agree with the gentleman, like we want covenant, all the things. But ARC is like Alex was saying, it's an amazing project because you can actually get quite far along the way in user experience without needing the covenant. And once you have that, it's like, okay, but now with the covenant, we can like improve this and this and this. And like you have these users that at that point, hopefully like when we launch this, will want those extra things. And then you have an actual, like you can showcase like demand for this, right? You can say, okay, this user are using this. These are the only pain points left. And with the covenants, we would fix this. And that's very different from like a project that can offer nothing without a covenant and everything with a covenant. Because for that project, it's way harder to like showcase like, hey, there is demand for this. Because you cannot really show demand, like other than like people on Twitter saying like, yeah, I want this, but you don't know how much they actually would use it, right? So
you need an economic signal.
Exactly. So I'm very excited about this ARC project because we can actually offer like a cool UX and improvement to the status quo without covenants. And then with covenants, we can just go all the way further to like what we really think is the best possible UX. I mean, within like what we have currently in our model. As it comes to covenants, yeah, any covenant would probably improve ARC. Like there's almost no covenant.
Didn't you make one of them?
Yeah. So I've been quite involved in like trying to get some of the covenants over the line. Like we've recently, like I was like pushing also for CTV and Toxic from Stack. We've recently tried to make like a technical like iteration on that makes it a little bit like Taproot native, which is called template hash. But it's kind of all the same thing, just in different technical implementations. I've also authored TX hash, but that's one is like more in a researchy phase.
One developer, two opinions.
Yeah, so like obviously it's like something that I created, but I also realized that it's not in a state where I would say we should go for this. So it's more of a research project. So that's why the other covenants, these ideas are way more mature. So I would say like, let's go with that first and then iterate from there. For like ARC specifically, it doesn't really make much of a difference. All the things that are currently on the table would help us a lot. So let's just do it.
Salvatore, what were the three things that you said were the ones you cared about?
Self-custody, scalability, and privacy. Those are the
okay.
Not tokens. That was the point.
I have like a list of 4 that include some of the things that you have. Mine are privacy, economy, like making it cheaper. I don't know a good word for making it cheaper. That's just one word.
Efficiency?
I don't know. That has other meanings for me. So privacy, economy, speed, and reliability. And I think like it used to just be the 3 until Lightning came along, and Lightning got 2 of them, but sacrificed reliability. And so now I have to add that in and be like, and I also want to make Lightning more reliable. So my list is 4.
I think like I'm talking more about Bitcoin property and how Bitcoin properties and how people use Bitcoin, while yours are more engineering trade-offs. So I think all matter, but like for example, efficiency and efficiently will help with scalability. So they're all in the same.
And just to build quickly on something that Salvatore mentioned, which I think is an interesting new dynamic in the context of software conversations. You can check out the work of a gentleman called Josh Doman, who recently put out this, and this actually probably the originator of the idea was Jeremy Rubin, who at one point built a CTV covenant emulator that effectively allows a set of parties to join a more trusted contract on Bitcoin and kind of like be able to trial, if you will, the enforcement of something that would be built with either CTV and whatnot. Now Josh is building in a similar direction, but I think ideally wants to allow for something very modular that can be deployed by anyone and use basically whatever opcode that they fancy. And I don't know that like this is the answer or something that's going to kind of like significantly accelerate the direction of the software conversation. But I think it's a very good idea. It's a very cool idea. This is something that we are also playing around with Arcade. And to be clear, like there's some limitations to actually how useful, like if you're deploying something off-chain using Opcat, that's not necessarily going to inform you about the usability and the feasibility of deploying something on-chain with Opcat, because when you're doing stuff off-chain, you have no concern over block space or block time. When you're doing stuff on-chain, it's a different perspective. But I think, I mean, I don't know whatever happened to that, but like Reindl over at the Taproot Wizards had conversation about, kind of like a toolkit for building cat-like programs, maybe in a more trusted manner or whatever. So I again, what I appreciate about this is it's something novel, and I think we need ultimately something novel to happen because certainly every soft fork has been different. And the conversation has been kind of like, in my opinion, going around in circle where, yes, there's iteration around the proposals, but there's not something really kind of like that shake things up in a way that people can really coalesce around and then create actual momentum. The latest, the biggest things that have happened lately is like kind of like show of hands and, letters and whatever. I don't think that really, like things like proof of work where people are actually deploying things in practice, and even if it's within a trusted context, I think is very, very cool. So I'm looking forward to stuff like this.
If anyone wants to win the hackathon, consider making like a 505 multi-sig that'll enforce, some random opcode that is proposed for inclusion in Bitcoin. I think that could be a winning project for the hackathon, and I'm a judge, so.
Okay, so we still have a few minutes, and I'd like to hear some questions from the audience. But first, just a quick round of applause for my fantastic panel. Okay, I'm going to run to them. Ladies and gentlemen, any questions? How do we scale Bitcoin? Are these guys going to help us? Any questions? No? Wow.
Handled it all.
No, nice. Apparently everything's fixed. We're good. Scaling's set and ready. Okay. Well, thank you very much.
Well, thank you.
Well, can we ask each other questions?
You have a question, Super?
No.
Do we have questions to the audience? Is that the question?
Go for it. Go on. We can have a couple.
Can we get? I think is there supposed to be like a fight between Barak and Steven? Can we maybe bring him up here and do a battle? Maybe that would be a good finale.
That's only for our premium subscribers. You'll have to tune in, get a subscription to the Insider Edition, and we'll see what can be done. But and the Ark is boarded 2x2. Thank you, Super, and it's also deboarded 2x2. So Super and Alex, thank you very much for joining me. Salvatore and Steven, thank you.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin Plus Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin.
All right, everyone, welcome to the end of day one of Bitcoin Plus Plus. We're gonna keep this shorter, about 40 minutes of chatting. Thanks. Maybe I can talk louder. I'll try. Yeah, so I'm really excited to have 3 really incredible, intelligent builders that are working on zero-knowledge related projects to scale Bitcoin. I have here with me Misha from, I'm gonna get this wrong, Alakanit. Okay, thank you. Liam Egan from Alpen Labs and Abdel from Starkware. So hello everyone, welcome to Bitcoin Plus Scaling Edition. Cool, so I think really awesome for the audience, maybe if we go through, just kind of down the line, you can tell us who you are, what you're working on, and maybe, what's another fun fact to give us, I don't know, what the first zero-knowledge proof system you worked on was.
Okay, well, I actually have an answer to the last question. I've done one back in the day, 2021, or like whatever called placeholder, that kind of stuff. Yeah, like all the names I do suck. So, yeah, sure. Okay. It's kind of that. Yeah, so what's going on, I guess, on my side, it's a little research initiative in terms of, it's called Allocated, sure. A little bit of a research initiative around Bitcoin pipes stuff. Trying to emulate governance or single transaction ZKP's verification on Bitcoin. The whole experiment involves, kind of attempts to instantiate witness encryption / functional encryption to do that. So it's like heavily experimental, very heavily experimental, okay? So, but yeah, I mean, that's kind of the end game, and I mean, we think it's worth trying. I mean, who else if not us? That kind of stuff.
So you're working on a research project that's using functional encryption or witness encryption.
Trying to emulate governance and the single transaction pessimistic verification of ZKPs on Bitcoin. Cool.
And what was the first, sorry, I missed it, the first time you worked on like a zero-knowledge proof system or like your first zero-knowledge proof?
The first thing, 2018 with Filecoin stuff. The first proof system I designed was placeholder in 2021.
Okay, cool. Very cool. Thank you, Misha. Liam, do you want to?
Hello. Okay. Yeah. Hi. I'm Liam. Chief scientist at Alpen Labs. We are making a Bitcoin rollup. Yeah. So I don't know. Probably heard a lot about this today. We want to scale Bitcoin using snarks. Yeah. First ZK thing I worked on. I don't know. I'll say Bulletproofs ++. It was my first paper. It's like it kind of co-invented the log derivative type lookups and small range proofs. So. Yeah.
And what year was that? That was like, I remember when this paper came out. You were working at Blockstream then, right? Or was this before you were at Blockstream?
Yeah, it was before I was at Blockstream.
Yeah.
I don't know, maybe 22?
Cool. COVID era project.
Yeah.
Okay. Yeah. Liam did zero-knowledge proofs in lockdown. No, I'm kidding.
Yeah.
But now you're out of lockdown and you're still working on proof systems.
Yeah. I have. I've done a bunch of stuff since then. These big table lookups, folding schemes. I don't know. Most recently, this Garbled circuits for verifying snarks on Bitcoin. Glock. Yeah. It's fun.
Cool. Thanks, Liam. All right, Abdel.
Hi, so I'm Abdel. I work at Starkware. So Starkware is the company that invented Starks, and we are building scaling solutions using them, specifically ZK rollups. And there are 2 aspects that we explore for Starks on Bitcoin. One of them is how to actually build a ZK rollup using them. And the other dimension is also how to use them in general for the Bitcoin ecosystem. Outside of just building a rollup, but maybe we can touch later. It can be stuff about IBD or building light clients or this kind of stuff. Yeah, and the first time I got involved into zero-knowledge proofs was when I discovered about Starks and Cairo. which is the language to build provable computation, basically. Yeah.
Cool. So all of you guys are working on systems to try and scale Bitcoin in one way or another. Could you guys maybe give the audience sort of an understanding of like where zero knowledge proofs fit in the project that maybe your company, your research project, or I'm sorry, research company in Misha's case, are building? So you guys are building rollups or like side chains, that sort of thing for Bitcoin. How is this zero knowledge proof systems that all of you guys have experience in, like where does that come and play in the scaling question?
Yeah, so like with a layer 2, you kind of could imagine it as like a kind of parallel blockchain with maybe different execution semantics or faster block times or something like that. And so we want to be able to use Bitcoin on the layer 2. And in order to do that, we have to bridge Bitcoin in and we have to bridge Bitcoin out. Bridging Bitcoin in is pretty easy. Bridging Bitcoin out is hard because you have to check that everything that happened on the layer 2 was carried out correctly. So the place that snarks come in is we can, instead of trying to get the Bitcoin blockchain to check all of this directly, which is not feasible, we can construct a proof, a zero knowledge proof, as people might say, like to attest to the validity of the layer 2. And then if this can be verified on Bitcoin, you can bridge out trustlessly. So we can't actually do this right now, but we're all trying to get as close as we can or potentially add soft forks to make it possible to actually do this.
Well, actually from my side, it's not like, you know, purely for scaling. It's more about just making possible to do more things on Bitcoin itself, kind of that. Just, you know, kind of pure L1 functionality enhancement thing, instead of like arguing about soft forks and upcodes and whatever. Dudes, come on, let's be real. You will never make a consensus, okay? Like, fucking, if you could have done that already. you would have done it already. You will never do that. So instead of like trying to achieve consensus or whatever, just whatever. Let's just emulate whatever we can, if we can. And this is effectively where, you know, kind of proof systems come as a compression mechanism, because, well, if you want conditional decryption, which pipes are all about, then well, you can't do straightforward whatever amount of computation, like within whatever conditional decryption scheme there is, whether it's like if it's some special purpose witness encryption or like special purpose functional encryption thing. All of those are very, very limited, and you know, on the borderline of if they're feasible or practical, but with proper compression and like with proper, you know, tricks and caveats here and there, whatever, the bet is that we could make it work. And that would effectively allow not just, well, you know, scaling Bitcoin and all the ZKP verification of Bitcoin kind of comes as a nice benefit of kind of introducing covenants to that. So that's where it is. I mean, yeah, it's that thing.
So you're working on introducing new primitives to Bitcoin using kind of zero knowledge proof-esque math, the functional encryption, witness encryption project, right? So your project has, I think, a particular viewpoint of how you're going to add more functionality to Bitcoin.
Scaling is just like scaling just comes at scaling, you know, product-wise speaking, whatever. If you want to focus on that, just comes as a, you know, a nice benefit out of that. I would say
Definitely.
It's just but
that makes sense. Yeah, I'd like to hear more from maybe Abdel about what is the Starkware. So you guys are building on Bitcoin. Kind of like Misha mentioned, we don't have a soft fork. Misha's on the opinion that we won't get a soft fork, it sounds like. So they're building ahead without it. What is Starkware doing? Like, how are you guys managing the fact that Bitcoin doesn't have the primitives to do ZK verification in script?
Yeah, right. So maybe I will start by giving a bit of history about how we are using Starks to actually build scaling solutions with them. So when Starks were invented, this was this idea that you can basically transform any statement into something that you can prove. But historically, it was very hard, like because you have this step of converting the statement to some arithmetization, polynomial commitments, and stuff like that. And initially we were doing that like by hand, literally, like you have a problem, let's say you want to build an AMM, and you need to think about how you can convert this statement into some polynomial constraints and stuff like that. And you know, engineers are lazy, so engineers in Starkware were saying, oh, we cannot do that by hand, we need to invent something to make it like more generic, more easy to build proofs. And Eli Ben Sasson, who is literally the inventor of Starks, was telling them, you will never be able to do that, but they still tried. And this is the genesis of Cairo, the language. And then they were able to basically implement this kind of CPU that has some instructions and stuff like that. And then suddenly you are able to prove any kind of program. But to write the program, you can do it in a higher level language. And it became much easier to actually build a program with that. And then we were able to build StarkNet, which is using Cairo, basically to implement the logic. So you can imagine that you have a virtual machine and you can implement smart contracts, whatever, and then you are able to turn that into Stark proofs. So right now this solution is deployed on Ethereum, and we want to be able to do the same on Bitcoin. But as you said, we cannot do it right now because of some lack of expressivity on the Bitcoin base layer that prevent us from doing a native ZK verification on Bitcoin. So the best that we can do today is what Alpen Labs and Citrea and all BitVM solutions are doing, is optimistic ZK verification. So this is something also that we want to do. So we want to be pragmatic. We know that it's probably not the endgame vision, but we want still to expand on Bitcoin even today. So we'll start by also doing some BitVM-based solution, and also at the same time continue to do some kind of advocacy, talking about the benefits of enshrining ZK verification into Bitcoin in the future. Yeah.
So you guys are moving ahead using BitVM to build out the primitives that you need to build using optimistic provers. How does that work exactly?
Yeah, so when you have... So you think of like a proof, a snark, as like sort of a universal verification primitive, right? Anything you want to check, you can convert it into a snark, and then you can just check the snark. So this is why they're interesting for scaling. But unfortunately, the verification program for a snark or a stark is too large to put directly into Bitcoin. So what we do instead in this kind of BitVM paradigm is called like optimistic ZK, or another name is kind of like a naysayer proof, is a technical term, but there's a prover and a verifier. The prover makes a claim that this proof is valid. Then the verifier, or the challenger, is able to identify an invalid proof and construct a proof that it is invalid, fraud proof. This fraud proof can be verified on Bitcoin. Even though the original snark can't be verified, the sort of refutation can be verified. And so in the case of BitVM or BitVM2, this is going to be like a fragment of Bitcoin script. And in the case of Glock or the garbled circuit style constructions, it might be as simple as a single signature. But in any case, there's some sort of simpler proof that your computation failed instead of checking it directly.
So it's, yeah, then that's what we call fraud proofs. And I think someone earlier made the point, that's like how Lightning works. Like when someone puts something on chain, you come back later and prove that what they put on chain is incorrect state, right?
Yeah. There's a whole family of like optimistic protocols on Ethereum, like optimistic rollups. Yeah, and it has like worse. I mean, like in a kind of vacuum, right? You prefer probably to just be able to verify the snark because it doesn't require this like third-party challenger to, be present.
Okay, so that's an interesting point. It's like, so what are the downsides of using systems like the BitVM optimistic verification? How would you call it? Optimistic verification or?
Optimistic snark verification.
Okay, optimistic snark verification. This is all new vocabulary, I think, for a lot of us.
There are multiple downsides. So first of all, you need to enable some time. So you have a problem of finality because you need to give a sufficient time for an honest person to challenge and submit a fraud proof. So that's one. So you have a problem of finality. Usually on the Ethereum world, it's 2 weeks. For the ZK rollup, it's instant. When you settle, it's already final from the layer 1 perspective. So in terms of UX, it's not ideal for users because they don't have finality directly. And also, like if you can have in the future like a pure ZK rollup, it's also better in terms of trust assumptions because it does not rely on economic mechanism to make sure that someone will be honest and submit a fraud proof. It's only backed by mathematical proof. Yeah, so it's also better from this perspective as well.
That makes sense. Yeah. So I have a question for you, maybe like a little bit more on it specifically, what you guys are building, and not a ZK focus. Like the snarks that you're building, like the programs that you're verifying, the content of those is going to be what's happened on the sidechain. Like, what is the work that these? Yeah.
Formally speaking, it can be anything. I mean, whatever you can prove, it can be that. If you prove state transition, sure, that's your thing. I mean, if you want to prove, I don't know, a Doom execution, sure. I mean, done that once, you can still Google that around. There is like a ZK Doom thing around the internet. You can prove your speed run, you know, that kind of stuff. So basically anything. It's all about if that makes sense.
I feel like building these zero knowledge proof systems as like programmers and developers, it's a different way of thinking about programming, right? Like, because you're proving that the execution happened in a particular way, right? Or that this program, if it ran, would produce a result. Whereas a lot of traditional developers, you're architecting systems that build things that then execute in a certain way, if that makes sense.
Yeah, exactly. It's a completely new paradigm. It's basically verifiable computation, but we wanted to make in such a way that from the developer's perspective, it's completely the same. It does not matter. We want to completely abstract the complexity of the zero-knowledge proofs. So the idea is that you can even build technically with a high-level language like Rust, and at the end of the day, you will be able to generate a proof of that. But it could be the same. It's just that the way you will verify it is not by re-executing the program in the traditional way, but by verifying the proof. Yeah.
It's worth mentioning for people who aren't aware, you can literally write Rust and prove that you ran it correctly. There's like a whole family of what are called ZK VMs. Yeah.
Or circuit compilers.
Yeah.
What? Sorry, a Servid compiler?
There is an old beef between ZK VMs and general purpose ZK VMs and general purpose circuit compilers. I'm just on the other side of this beef. I'm on the circuit compiler side.
Yeah, and for us, we are in between those two, because there is also another alternative, which is Cairo, which is like you build a VM, but that is specifically designed to be ZK friendly. Because as Liam said, it's true that you can technically prove Rust, but it comes with some overhead in terms of performance, because Rust, specifically RISC-V, it was not designed to be ZK friendly. So you can do it, but it comes with some overhead in terms of efficiency.
Yeah. I did like one interesting flavor of this for people who are interested is like, suppose I have a program that computes a square root. Computing a square root is fairly complicated, but checking that I have a valid square root is very easy. You just multiply it. Yeah. So there are a lot of cases of this where verifying something is easy, but computing it is hard. So if you're doing something by hand, or if you have a really smart circuit compiler that can figure these things out, you can do it the easy way inside of a snark. But in practice, things are fast enough, like they've improved in performance so much that unclear, like you probably don't need this depending on what you're doing.
What do you mean by need this? Like, what does this mean?
We can kind of do it the like dumb way, like prove Rust. It kind of
Wait,
works.
okay, when you say prove Rust, you mean prove like the execution environment of Rust?
You have a program start state, a program end state, or input and output, and a program, and I can prove that like if you run the program with the correct semantics on this input, you produce this output.
Yeah. What does it mean to prove that, though? Sorry, maybe that's like a weird question.
Maybe I can try to explain. So technically, you don't prove Rust, but Rust compiles to, for example, RISC-V. So it's a set of instructions. And then for all those instructions, there is a circuit that is able to prove the instruction. And then you compose this, and you are able to prove the execution of the program, basically. But it's functionally the same as proving the Rust program that you wrote in the first place. And Liam is saying that basically it becomes faster and faster. So at some point, he's arguing that there is maybe no point in going lower level. So our approach and the approach even lower, that is writing directly specific circuits, I have a slightly different opinion on that, but it makes sense. It's true that it becomes faster and faster. The caveat mostly is probably about the cost, because even if it's faster, there is also an overhead in terms of the proving cost that is non-negligible.
What does a proving cost mean?
The off-chain proving cost, because you need to run some machines to be able to do the whole mathematical proof, and it's quite heavy. And especially if you are not proving something that was designed to be ZK friendly in the first place. Yeah.
You can measure it in dollars. Yeah, like, how much does it cost to rent N GPUs for this much time?
You can even create markets around proving. There we go.
Okay, so if we're gonna bring this kind of technology to Bitcoin, what are some of the benefits that we would see in terms of writing locks or programs for Bitcoins, if that makes sense? Like, I guess what are the benefits, and then I guess my follow up is gonna be like, what are the downsides, like the costs, the trade offs? Like, are these gonna be like? Are they bigger? Are they small? It sounds like they'd be bigger, but you get, it sounds like maybe more accessibility. Like what are the parameters that we're looking at here is like why this is even an interesting thing to talk about at a Bitcoin conference?
Yeah, I think there are a couple of caveats in terms of costs, kind of trade-offs in terms of costs, but there is also a little bit of a thing which I don't see a lot of people talking about. Like, let's start with costs. So obviously, kind of whatever on-chain execution, whatever inside the interpreter with a certain opcode is always going to be mostly the cheapest out of all of the options, right? But as I said, we're not getting it. Like, forget it. Effectively, the best thing you can do is you can just try to compress whatever computation you can do. Like the next cheapest thing is you can try to compress whatever computation you need to do into like a ZKP, and then do maybe a conditional decryption, like ideally with pipes, maybe like optimistic verification with like fraud proofs, and it all comes down to like the cost of this proof verification. Like with pipes, for example, it's just the cost of a signature verification. So the signature verification, what is it like? I don't know. I don't even know. Like at this point, like I don't think anybody knows. So that's the thing.
But it's pretty cheap. And
it's
like
very cheap.
Basically, anytime you spend Bitcoin, you do signature verification currently.
Yeah,
so it wouldn't be the pipes that you're building wouldn't be a departure from the existing way that we're spending Bitcoin to the large extent in terms of cost on chain.
Moreover, once this is done, you could even try to start simplifying Bitcoin. You could start disabling opcodes, actually. I mean, come on, guys.
We'll get back to that. No, that's. I think that's a spicy. I think that's a provocative statement. I think
absolutely.
It's always, okay,
yeah, you could replace Bitcoin script with a snark.
Yeah, basically. Yeah. So that's the advantage, is you don't have to write Bitcoin script anymore to some extent.
Yeah, or I mean, I don't know. Advantage, disadvantage. It's a thing. Yeah.
Yeah. So for me, in terms of the benefits, so as we said, scaling, so cheapest transactions and also way bigger throughput, like thousands of TPS, sub-cent transactions, but also some aspects that are less discussed maybe will be about UX, because if you are able to build rollups and layer 2s, you can have way better UX and still be self-custodial. For example, you can implement something called account abstraction. This is this idea that you don't have to do only like signatures to authenticate to the blockchain. It can be whatever. And in particular, it could be something as simple as Face ID authentication. So you would literally sign your transaction by just unlocking your phone. And this is not theoretical stuff. This is something that we have in production today, not on Bitcoin, because we cannot settle on Bitcoin. But if we could settle on Bitcoin, we could also have this kind of UX. And also two more stuff that I can name is privacy. Because you can have some privacy, actual privacy on the layer 2. And maybe something in the future that can be interesting is about quantum resistance. This is something that we explore, like how we can use Starks to build quantum resistant signature schemes or this kind of stuff. Yeah.
I want to second the privacy thing. I think one of the biggest problems with Bitcoin is that it's not private, and this breaks fungibility of Bitcoins. And that is like a huge existential risk. So like the lack of extensibility and the lack of privacy means that people generally use like centralized third parties to do stuff with Bitcoin, which, as people do that more, empowers these third parties to impose KYC type sort of arbitrary restrictions and sort of breaks the permissionless ideal. So like we need privacy, and I think people should be able to do like what they want with Bitcoin in a way that does not empower like these centralizing third parties.
Coming to the UX part of things, there is also this little nuance that whatever you can do is kind of limited by how do you settle on Bitcoin, as Abdel said. Like if you settle with, I don't know, within several weeks, or like with a couple of fraud proofs, or like with a couple of transactions, etc., it kind of limits you to what you can do. Because let's say you have came up with like whatever, some shitcoin on Bitcoin, okay, and then these people just suddenly start contesting the transfer of that shitcoin, and that's going to be a shit show, even worse than it is like anywhere else. And I mean, imagine that's completely ridiculous. But anyway, so that kind of stuff, and you can't really do that kind of, crap on Bitcoin if the verification is not pessimistic and like a single transaction one. So it's kind of that.
Yeah, I was talking in the case where you could verify natively the proof. Yeah. So, and for that we need a soft fork, to be clear. Yes.
Cool. So some of the advantages of adding a like ZK system to Bitcoin, whether through BitVM or pipes or a soft fork that gives us more script native ZK verification. Sounds like the benefits are privacy, scaling in terms of being able to build. Sounds like some of the privacy comes from like side chains. Does that make sense? So you transact in a different system and then you verify that the things that happened on chain.
Yeah, I mean, there's kind of two applications of ZK in blockchain. The first one that occurred was like the Zcash style zero knowledge proofs, which keep data private about the transaction. And then the second one, which we've been talking about, is like this scaling thing where you can check a lot of stuff, compression, very efficiently. So for the privacy, we're talking just kind of about both, but like the private transactions part, which is not possible on L1, but would be possible on like a L2.
So you could build a more private L2 transaction system, and you could transact with Bitcoin in this side system, so to speak. And then if you ever wanted to take your coins out of the side system, you'd be able to do that using a snark or like a proof to exit, basically, is my understanding.
Yeah, and with native snark verification, this could be entirely trustless. So like anybody could do it. You don't need an operator or like a third party to help you, and that would be kind of like the ultimate vision of.
And so where we are currently is you have operators or systems, like basically, they're not trusted parties, but it's like a quorum of people that you kind of need to agree that what's happened is correct, or?
I mean, they're trusted in a sense. They're not like it has slightly different properties from a multi-sig, or very different, I guess, depending on your taste. But they're like they are trusted, and like if all of them were coerced, then it would be impossible to do a withdrawal out of an L2 with operators.
So that introduces risks into using these systems to improve your privacy, and the risk would be that you wouldn't be able to bring any Bitcoin value that you had in the side system back onto chain to like your own, back to like the layer one system, so to speak. Cool. Okay, so, sorry, if you have
I just wanted to provoke you more with, I mean, come on, fucking somebody throw a potato at me, whatever. Like with, as close as we can do, like to the native ZKP verification of Bitcoin, whether it's again conditional decryption in any way, like one could probably do privacy for Bitcoin, like right on the L1 itself. We'll talk about that in the next series.
Okay.
In the next episode.
Tune in for episode 2. Cool. Okay, so I think we've talked about some of the benefits of adding it. I guess what would be the downsides to the system? So it sounds like the systems that you guys are using, some of the downsides are that, right now we don't have verification at the layer 1, so we've invented these kind of side systems or like secondary proof verification, optimistic kind of checking systems. Yeah.
One downside that rollups specifically have is the problem of data availability. Because when you have your ZK rollup, you need to submit the state diffs to Bitcoin. And because Bitcoin is not optimized for this data availability problem, unlike Ethereum, for example, that has a separate ways of submitting data for rollups. So this is a problem on Bitcoin because it's expensive. And also, if you start having like 2 or 3 ZK rollups, with 100 TPS each, they can submit and fill the blocks. So that's one issue. Unlike, for example, scaling solutions like Arc that don't have this DA problem. So this is one big downside of ZK rollups.
I apologize for laughing. You're talking about putting data in the blockchain and. No.
Come on,
It's
come on, just raise the fees for up return. Just raise the fees for inscriptions. Don't fuck around with those.
Yeah, we were talking earlier about Misha made a comment earlier. We were talking about how one of the things if we get like a ZK prover or verification system such that you could do it natively in Bitcoin, basically that would turn Bitcoin blocks into data storage more so than they are currently. What do you guys? You guys are nodding? Is that correct? Is that?
I mean, technically it's correct because you submit arbitrary data that from the point of view of the layer 1 could be considered as spam, but because, in my opinion, it's useful spam because it can enable Bitcoin as programmable money, but you know,
make people pay for it. Let them spam and make them pay for it as much as possible. That's it. That's your solution.
You could put it somewhere else if you wanted to. Like you could make what they call like a Validium or something, but yeah.
What's this data that we're putting in the so like what's the trade? So we're no longer putting scripts and programs. Like and now we put scripts in the put programs in the blockchain right now. No one talks about that, but when you spend Bitcoin, you're putting a whole script or like a partial of script if using Taproot in the blockchain, right? And that's part of the verification is revealing the actual program that you had to lock the coins up to, right?
Yeah. So the data we need to publish. So there are 2 ways of doing. Either you need to send the representation of the compressed data. So first of all, when you have your layer 2 system, a ZK rollup, you will settle time to time to the layer 1. Let's say you do that every 6 hours, for example. So you need to submit a representation of what has changed between those 2 settlement time. There is 2 ways of doing that. Either you submit the compressed transaction data, or you submit the state diffs. Basically, the state diffs is what changed. Like imagine your site system is a blockchain with a state, and you have some changes in the state, and you need to submit a representation of the changes. This is what we do, for example. State diffs is much more efficient and compressed, and this is what you need to submit. In order to make it fully trustless and to fully inherit the properties of the layer 1, you have to do that, because only then you can verify that the state root is correct and that the changes are valid according to the proof. But as Liam said, you can have some hybrid model where you do like Validium, where you submit those data elsewhere, so it's off-chain, but you have a bit less security because you don't fully inherit from the security properties of the layer 1.
Just wanted to say that you could again just think we haven't really formalized yet, etc. It's just whatever. We really just brain dumped that thing like a couple of months ago. With pipes, you could probably keep putting scripts on Bitcoin instead of random data. But yeah, like whatever.
The pipes project that you're working on isn't quite the same as the zero knowledge proof stuff, right?
Zero knowledge proof verification is a nice consequence of that. Let's say it this way. It's a nice side consequence of that. I mean, it gets you ZKP verification within a single transaction, but that's just the way. But that's just because of how you are basically forced to construct conditional decryption, because there is simply no other way, kind of fundamentally. So it gets you ZKP verification Bitcoin. So but it's a consequence of it.
Okay, so the pipes project you're working on would get people ZK verification without a soft fork, which is cool. But you're still figuring out exactly how to do that.
No, I mean, okay, well, the formalized construction, we were hoping to publish it like by September. I actually even teased it to Liam, but like we did not. So
Okay.
it's, I mean, let's just be honest about this, okay? We are actually working on security proofs. That's what it is. Like security proofs is like what takes us, it took us like several last month or something.
Interesting.
I just wanted to emphasize that putting snarks on Bitcoin is not like, I mean, it would require putting like a small amount of data, but it's not like the amount of data we're talking about is really a consequence of a roll up. Like if you're doing a bunch of stuff on an L2 and you want to inscribe that into Bitcoin, that's where the like large majority. So there are other things you might want to do with snarks that might not require putting data on L1.
Can you give me an example?
Smart contracts, like I mean, like other kinds,
Stateless?
like some kind of lending thing, probably like
It requires state.
between two people.
Who the hell leads that?
An example maybe would be like what I mentioned before, like quantum resistant signature schemes. Like you could do some signature aggregation and batch this into zero-knowledge proof, and you don't require a state for that. So you just have the size of the proof for this.
That's, I mean, so like when you guys are talking about like I don't know if the zero knowledge, I mean, I'm sorry, I don't know if the quantum resistance is this, but it reminds me of cross-input signature aggregation to some extent. Like, is cross-input signature aggregation like in the same realm of like, I mean, it's not snark proofs clearly, but it is a similar batching technology,
It's
right?
the same idea of batching, yeah, kind of, yeah. Conceptually, yeah.
Cool. Okay, we have a few minutes left. Is there anything that you guys want to, I guess, like, what am I trying to say? Like, what do we want to leave the audience with about, like, zero-knowledge proof stuff? Like, we're working on it. There's a couple different ways that different projects are in process to bring the power of snarks and verification to Bitcoin. You guys are using BitVM. Misha's working on a quite ambitious project to use pipes to do that. What, I guess, like, what's this, like, what's the, like, I don't know, radical zero-knowledge proof future that we end up in Bitcoin? Like, is it going to change the way that people are using Bitcoin, or is it, like, all going to be the same?
So for me, I would like to have to see more discussions about the usage of zero-knowledge proofs outside of even the discussion of building layer 2s, because we can use them for so many different things, like instant synchronization, like clients, or for example, for Cashew, for Nostr, for many places in Bitcoin ecosystem, and also the symbiotic ecosystem to Bitcoin, or for decentralized mining, for example. And this will not require any modification to Bitcoin, and still you could benefit from this. For example, we did an experimentation with Stratum V2, because in Stratum V2 you have a problem because you have the miners, the individual miners, they have to either send the whole list of transactions to the pool or not, but if they don't, the pool has to trust that the miner has built a valid block and that the coin base is valid and stuff like that. So we did an experimentation where the miner can generate a proof and the pool verify the proofs. And it's better for them also because the miners don't have to disclose their strategies on how they are building the blocks and stuff like that. Anyway, TLDR is that Stark proofs and ZK in general for Bitcoin can be used in so many different places. So I would like to see people taking more time to see where they could be useful for Bitcoin.
I guess, okay, this is a good final question. Where can people go to learn more about how to build ZK, how to learn about it? I feel like it's I mean, it's been around for a long time, but I feel like the general population understanding, especially in devs, of how to build and use them and what kinds of things they might be useful for. Where would you guys send people to learn more about, like, how to build them, use them, that kind of thing?
I mean, if you want to use ZK proofs, probably some kind of ZK VM, either like SP1, RISC-0, Cairo, I don't know, Noir. There's like a bunch of different ways to do this. Yeah, that's by far the easiest way to start using zero-knowledge proofs.
Cool. Any final comments?
I think that if snarks and zero-knowledge proofs had been in their present state when Bitcoin was conceived of, the world would be a vastly different place. Like the synergy between like snarks and blockchains is like one of the most perfect matches I've ever encountered. I mean, it's so rare that you get something like privacy and scalability at the same time for free from one thing. Like usually you have to trade off everything nice.
Yeah,
And
this synergy is literally the content of my talk on Friday. It's insane. I agree with you. This match is so perfect that it was written. Yeah.
You want the final comment?
Yeah, I love the final comment.
Reduce the block size, remove opcodes, raise the prices for inscriptions. And now you're gonna fucking kick me out of here.
Cool. All right. Well, should we do time for questions? Maybe we'll get like 2 or 3 questions if anyone has anyone for our panel about CK stuff or what they're working on. Yeah, go ahead, Zia.
Okay, I'm gonna leverage my access to the microphones to ask a question. So, that last comment, the one before that. So, talking about, I know that this panel is mostly about like ZK and scaling. But it's nice to talk about the privacy, and you guys did mention a few comments about the privacy side of things. So I was thinking about if the use of privacy, or actually if the use case for privacy in some of the rollups or some of the, like whatever we call them, like the other external monocultures that are connected somehow to Bitcoin, if any of that use will be like brought down, taken down, and will that be like impact users in any way? Because you, Abel, did mention something about like the data availability. So I was like, so we see like privacy projects being taken down these days. So, and I'm really interested in that topic. So,
yeah. This is why we need those systems to be fully trustless and permissionless, so that it's not correlated to one entity, and they cannot be shut down technically, like, because it's just a set of arbitrary programs that anyone can access. By the way, I did not mention that in the potential downside of rollups, but it's a bit related to that. You have the problem of governance in terms of the smart contracts that verifies the state transition of the rollup and so on. Because, for example, right now, what we have is some upgradable contracts. So you have discretion on who is able to upgrade the contract and so on. You have to choose. Either you make it completely immutable, and then it's forever, and it's completely trustless, or not. But it's risky, because if there is a bug or something like that. So there are trade-offs, but the best way for it to become unstoppable is to be fully permissionless and trustless.
My perspective on this is that Bitcoin is an inherently political technology. So in the conception of Bitcoin, right, like it's seizure resistant. It's a digital bearer asset. Unlike bank money, like there's no special hook for the government to take your Bitcoin. So when we're asking ourselves what the impact of building privacy technologies is, I think we have to keep in mind that everything we're doing is political. So if we want this, like we have to acknowledge that, but like not let it stop us, like, you know, so.
I will probably not get a round of applause after this, but anyway, like those privacy projects you're talking about, which are getting shut down. I mean, well, let's be honest. Like, small boys get pushed around all the times. Okay, like you can't push around Bitcoin. If you make it private, it's gonna be there. Whatever, it's not gonna get pushed around. And that's basically it. So just make the L1 better, I would say, and like just make the Bitcoin private itself by any means, and you're gonna be good.
Mostly referencing the sequencers and the borders themselves. So
Zia said
that's the different stuff.
Zia said he was mostly referencing the sequencers and the verifiers themselves. Sorry.
Yeah, so again, make it permissionless. Like, if anyone can be a sequencer, you are fine, actually. Yeah. So for example, right now, we literally yesterday moved from a centralized sequencer to a decentralized sequencer. So you can have different models, but for us, it's a variant of Tendermint, which is a BFT consensus. But you can do whatever you want. It could be even proof of work, actually. You can even think in the future about some merge mining stuff, where miners could also be sequencers and provers. You can do really what we want. Yeah. But again, the best way is to make it permissionless. Anyone can be a sequencer, anyone can be a prover, and you have a fee market, and anyone can generate proofs.
Cool. Do we have one more question, I think?
I got another question regarding publishing data on the blockchain.
Let's go for it.
Deep down, everyone here wants to use the Taproot annex. That wasn't mentioned yet. Do you have any opinions on that?
It's not specified.
You are provoking people for like to throw cabbage at us, right?
I mean, yeah, I don't know.
It's not specified really.
Yeah.
No.
Same.
Anyone else?
Cool. Thank you, everyone. We'll see you back here tomorrow at 12:30 for the hackathon. So.
An ancient city where empires met to bridge ideas that changed the world. Today, a new current moves across the Bosphorus. At the center of the world, in the city of bridges, builders gather to scale Bitcoin to the world. Bitcoin ++ Scaling Edition, September 3rd to 5th, 2025. An ancient city where empires met to bridge ideas that changed the world. Today